Okay, so we apologize for issues. We'll try to speak from this microphone until the first block. To maybe we can put this closer for the proper sound. Yeah, it's working. Okay, we'll switch the camera for the presenter view, and in the meantime, let me open my slides. Can you see my screen and myself also?
Io poi ci ho parlato, però abbastanza fuori dal mondo, cioè ha avuto delle reazioni che non mi sono neanche piaciute, penso siano, che siano state anche antipatiche per papà, e che ieri lui si è arrabbiato perché...
Also, Salvatore, you can have a seat.
Allora
the first row or something.
Bisogna pagare pure le commissioni.
Shall we start?
Io neanche mi immaginavo.
Yeah, I think so. Since we have some technical issues, let me shorten my talk and to give the stage for the others. So I just wanted to welcome you here. I already summarized what we have in the coming hours. The first block we have introduction on the course action itself, and also the two plenary talks. One from Francesco next from online, and also James Dietrich from here. And then we will do a coffee break, and then we will try to fix the technical issues. And then we will have the summaries of each working group of the action. So this is the thing that maybe I can provide you later on, an introduction of our institute, consisting of 5 different departments, and we mainly working on teaching earth sciences related courses, geography, bachelor's and master's, even Hungarian and English language, and also we have PhD level of studies as well. And how our drone research focusing on, and why I was involved, we are mainly working on mapping of fluvial geomorphology, and because drones are really nice flexible tools that they can serve as a really great data collection method to have high resolution data sets on the river morphological changes, and we can monitor the changes of river channels with intensive bank erosion. This is the slide that I would like to move on. And the next thing that, for example, we started in collaboration with German colleagues in Dresden to apply thermal infrared cameras, also not to just map the morphological changes, but also to involve some velocimetry, image-based velocimetry methods to analyze the river flow. And also now you can see in the left side, thermal infrared cameras can serve as a nice additional tool when the traditional optical velocimetry methods cannot show something interesting at right side. Thermal cameras can add additional information. Also video mapping of aquatic vegetation. As you can see on the bottom of our fleet, we have several drones at the moment that we apply, even RGB, thermal infrared, multispectral sensor systems. And also we started a new research area, monitoring of soil moisture estimation based on also thermal cameras and multispectral cameras, that I will talk also tomorrow on working group meetings. So let me give the stage for Brigitte Todt for another welcome words.
Thank you. First of all, we would like to say thank you to have the possibility to host the meeting here in Hungary, and special thanks for László and the Debrecen group. So my name is Brigitta Todt. I publish my maiden name, which is Brigitta Szabó. I am working for the Institute for Soil Sciences in the Agricultural Research Center in Budapest. I would like to shortly introduce our institute. Just a minute, because they try to fix something on the laptop. Okay, so let's see. Okay, I cannot move on, but anyway, maybe free talk. So our institute has 4 departments. One of the Department of Soil Biology, and then we have a department which is focusing on fertilization analysis. They work with wastewater, how to apply it on agricultural field, what effect it has on the productivity. Then we have the Department for Soil Physics and Water Management, and this is where I work. There we focus on how to map soil hydrological properties, and we work with the hydrological models. Then we have a department which is dedicated for soil mapping. There, I thought to show you a web page. Okay, so I run a little. Okay, now I can even present it, but let's move on. Anyway, I should not use too much time. We are a little bit in delay. So I just would like to highlight a few works which belongs to our institute. So we have a website where we publish the soil maps in 100-meter resolution in raster format, and it's nice that we can provide the information about the texture classes, the particle size fractions, soil organic matter content, pH. Then we have information about the soil types, then the rootable depths of the soil, and we have some information about secondary soil properties such as soil organic carbon stock and the saturated water content at field capacity, water content and building point. This is under construction. We have derived these maps for the catchment of Lake Balaton, but we would like to increase it for a national wide. And then this is the platform. We try to make it as easy to use as possible. The depths of the soil layers are from 0 to 5, 5 to 15, 15 to 30, 30 to 60, 60 100, and 100 200 centimeter. It is the national standard right now. And why I show it? Because of course, we are thinking about how to use spectral data, how to use that to refine this kind of information. Then another work that I would like to highlight is that we are partners in the EGP Soil Horizon 2020 project. There it's an interesting work how the Lucas topsoil data could be used together with national soil data. So our team with other international teams are working on how to use these two different databases. We know that all the methods are different, even the sampling depths. So how could we do the best from these and use jointly? And another work is that the group of the digital soil map, they contributed to the global map of salt affected soils. It was an interesting work because there, of course, they had to focus on how to map those kind of soil properties which change jointly. Then another work which can be interesting, that we updated the European hydraulic transfer functions. It is available through a web interface and also in an R package, and it is derived on European hydraulic data set. And at this stage, we focused on also the available water capacity, and we used the random forest method, so we could provide uncertainty for the predictions as well. Okay, and then some drone issue that just a kind of like feeling about the field survey we had last week with many of the harmonious participants. It was in Italy, in close to Sele River, and you can see my colleague János Mészáros. He's using the Kubert hyperspectral camera and performed the survey with it. And the other thing which is an important project now in our institute is the Octane. This is also a Horizon 2020 project. There our aim is to analyze the effectiveness of soil water retention measures. We use catchment scale models and soil profile scale models, and in this project we try to contact the local stakeholders as well to find the best solutions to retain water and nutrient in small agricultural catchments. Thank you very much for your attention.
Share the screen.
Thank you, Laszlo. Thank you, Brigitta, and good morning to everyone. I have to say it's a big pleasure to start this session. We had so many complications during the last years and during the last months, weeks that we really do not expect. Nevertheless, this has been a great experience and a very good project I mean, based on my personal feeling and based on everyone perception. And I will try to summarize what have been achieved in very brief with this group of people. Here is just a short list of the main participants, the most active ones, but in the reality, there have been more than 150, 200 people that have been rotating around harmonious cost action. What is the aim? The aim is to exploit the use of drones, or as we usually say, UAS, to monitor a hydrological system and the different aspects of the hydrological system, starting from the surface and moving toward the river network and components of the river network, evolution of the river and stream flow. Not only that, because our intention is to go beyond the stream flow only. This is mainly a perspective. What we understood when our colleague opened the session this morning, he said UAS was almost a bet for the department. In the reality, there is a lot of potential in this small device. And now it's clear to scientists that this is one of the device that could help support health monitoring, providing a new tool to fill a gap existing between field observation and satellite observations, which will be always there, that are increasing their accuracy and resolution with time. Think about the use of CubeSat more recently. But the drones can provide really the tool to validate remote sensing data and to reach a resolution that was never expected 10 years ago. What is the what are we doing with what Harmonious have been doing? Essentially, has been promoting the use of this technology in science. And the first task that we have been tackling was try to identify clear guidances and protocols in the use of drones in different contexts. For instance, our action is structured in 4 working groups that will meet tomorrow. Each of these working groups has been led by different researchers that are interested in UAS data pre-processing, in vegetation monitoring, in soil water content monitoring, stream flow and river morphology monitoring, and also we have one final working group that is trying to summarize in one container all the information that have been gained by the action. And this is the last deliverable that I will introduce to you, one of the last. The channels used by the action have been several. Here you have almost the list and the links of each of these channels. Here we have a photo of the beginning, and probably we should have also one of the closure. I think we will discuss through today, through the coming days, that of course this is not the end of the activities of the Harmonious Group, because we started in Valencia more than 4 years ago, more or less. But this group has been consolidated throughout the time, and now we have additional projects that are ongoing, and new projects that have been submitted that will certainly keep this network of scientists alive throughout time. For the different topics, we will see there are different problems that have been tackled. One is the issue of the data pre-processing, which is a problem with the management of drones. Another one is the use of drones for vegetation monitoring and precision agriculture. And in this, we have achieved some successful results. We have been also working on the use of drones for retrieving soil moisture, and this is, for instance, the quality that could be achieved with the use of drone with a differential method for the estimation of the soil water content. We have been working on the description of 2D flow velocity maps in different contexts, and in this, one of the an interesting outcome of the project is this paper published in, if I remember correctly, 2019, which was aimed to collect a number of subset of data to be used by other scientists to train and test different methodology for image velocimetry. This is an example of application of these different methodologies in order to identify the most appropriate in a specific context. Of course, here there are no figures about all the activities involved in the publication of these papers, but in the reality, these papers are all the result of an intense collaboration, and in most of the cases, this collaboration was very successful when it was in presence. At least probably this is because of our habits or way of working, traditional way of working. This is another result of very interesting achieved within the action, that is an index that was developed in order to identify the optimal window for image velocimetry application. This is a study that was done also in 2019 about the use of the definition of accuracy of a DSM and the suggestion of potential strategy to increase accuracy of DSM just using drones and flow paths. And finally, this is something that represents the final result. I will go, since we are running out of time, I will try to be very fast in the description of this last contents, but essentially this is the last one of the last outcomes deliverable that have been obtained to provide a number of guidelines in the use of drones, because this is necessary because the number of information and the number of consideration that should be taken when we fly a drone for UAS mapping are significant and require an enormous amount of knowledge that cannot always be available from just one person. So our suggestion is to split the problem in 5 pieces, and according to these 5 different pieces, we have identified the best references that could be used to approach a UAS mapping properly. Or there are also in the paper a number of comments and suggestions to avoid common mistakes. What is important is also to provide and to have a method and a number of checklists to avoid errors during the fly and before fly. This is something that also we have been trying to provide to the users. And also another point that is very interesting and important from my point of view that we have been stressing in our activity is try to build reference metadata associated to each flight, because when we publish our UAS map, sometimes those cannot be compared with others if we don't have all the information that have been used or all the characteristics of the flights, the information about the sensor used, about the flight plan and so on, which could make it useful for other scientists. Another element that have been extremely useful from my point of view is this. There was some link here, but it doesn't work. Okay. We also collected in our YouTube channel a number of lectures on different contents that could be used by students, PhD students, postdoc technicians to deepen some information about different procedure and different problems in US-based observation. Finally, okay. Finally, in our last task has been accomplished with the closure of a book that will be published by Elsevier this year. This book will collect all the activities and the experiences that we have gained during this almost 5 years, I have to say, of this cost action. This is the final structure of the book with its chapters, and I have to say that I mean, we are very grateful to the Harmonious Cost participants to provide such a great quality contents for this book. Last but not least, one of an interesting and extremely useful outcome of the project, and I will close with this slide at this point, is the interaction with the EASA. EASA is providing all the regulation for US users, But what is missing and what was missing since now was some protocols for the use of drones in different applications. And just in the last year, we focused on how support EASA in this process. And we actually have just finalized a manual with operation or information and suggestions and emergency response plan that will complement the regulation provided by EASA. Essentially, we have achieved most of our objectives, and we probably have achieved more than what was really expected. And I really think that this final workshop might be stimulating to identify the path for the future in the use of drones. So I close with this, and I thank you all for your attention.
Yes, we
can hear you.
Okay, yes. So thank you for this opportunity to present my work. I know that this is or it looks quite different from the general aim of your interesting project, but I still believe that maybe in 5 years from now, other application using real-time processing will also be used for your application, because this really gives a possibility to let's say to have a higher level of detail of the information that you get, and in some application can be useful. So the presentation of today really wants to give a very brief overview. We don't have much time on the UAV technology and how the real time. Can you hear me well? I hear the echo. Okay, that's right. The real-time UAV semantic mapping. So, what are the possible solutions that makes your drone, your UAV, something that can deliver information in real time, and what are the current solutions with the pro and cons? And also, I will give briefly some overview of what are the next challenges that we have to face. So just trying to summarize, basically at the moment we have drones that are able to fly, let's say from 30 minutes with rotor drones to up to 2 hours with a fixed wing. It depends, of course, of the payload and the size of your drone. So can be, these are, let's say, quite optimistic values. And we have, let's say, flights that are overall reliable. And yeah, we have already seen in the previous presentation that nowadays we have a lot of small sensors, or at least lighter than 5 years ago, that can be really embedded on a drone. That's really a big advantage that we have seen, a big progress of the technology in the last years. And of course, there are a lot of customized solutions that are popping up every year. Maybe they are not very affordable, they are quite expensive, but still things are progressing. And as it was mentioned in the previous presentation, most of the country, and especially in Europe, have regulation nowadays. So there is more clarity on how to fly a drone. So if we look at the UAV mapping in general terms, there are main challenges. Can you hear me? Is it just my problem, the echo?
We also have some echo.
Yes. Well, okay, let's try. So there are two different typologies of UAV mapping. One is the classical related to structure from motion to or photogrammetry. So really about the geometry, the 3D reconstruction, let's say, of what we acquire with the images, with an accurate georeferencing and mapping of this information. Or still the registration or the use of multiple typologies of data. So to integrate the UAV acquisition with satellite data, with terrestrial data, in order to have a better information, but still the geolocalization is the main aim. And then there is the second typology that I call semantics, that can use traditional machine learning or in the last years deep learning methods in order to automatically extract information from the data that are collected, using maybe more than 3 bands, like in the case of hyperspectral or multispectral. Of course, these two typologies of acquisition basically follow the same scheme. So we have an acquisition, as discussed before, that must be done according to some rules, according to the aim of the flight. We have some processing at home or in the office of the data, and then we have finally the delivery of the results. Of course, in many acquisition, the accuracy and the completeness of the data that we provide are really the aim, but there are other applications where this kind of aspect is not so relevant, and very often we still rely on commercial solution, at least when we look at the structure from motion. So Pix4D, Agisoft, or OpenDroneMap can be possible solutions that are used. But are these applications, are these solutions always suitable? And in general, this traditional way of seeing the things follows the traditional division of the different domains. So we have photogrammetry and remote sensing on one end, then we have the robotic part when we add some information, and still there is a strong component in the last years of computer vision with the arrive of these new deep learning algorithms that are somehow changing a little bit the use and the processing of our data. But still, these are well defined and well divided. Overall, there are, especially for monitoring, a lot of things that are going on the market. So if we look at the stakeholder perspective, still the data acquisition is very often given to an external company, and we need some dedicated person to pilot the drone and then to process the data and then to interpret them. So there is still a division of this aspect, although the automatic processing is somehow making the differences and the gaps between these different professional figures much closer. So if we look at the application and the market for real time, it is really growing in the last years. So there is a growing number of applications, especially related to urban environment, but still also for natural monitoring purposes, that wants to, let's say, to look into the automation. So the possibility maybe to have a recharging platform to take off and land the drone from the same position, so to perform multiple flights at the same time using the same drone, and the possibility to connect the drones to larger network in order to do the processing maybe in remote. And this kind of application can be used first of all for infrastructure monitoring, but still also for precision farming, search and rescue, and many other surveillance or monitoring applications. So these are still at the beginning, but they are growing, and maybe in the next future this will represent a big change. So what we did in my faculty, in our research group, was really to try to conceive some first real-time 3D semantic mapping acquisitions, where at the moment they are still simple. We still use small drones and RGB cameras, so we are not really working on something that can be directly used for your purposes. But in general, the idea is that we have basically an acquisition of images and the videos from the drone. These information are then processed on board or stream somewhere in remote, and there are basically two processing that are happening in parallel and hopefully in real time. So the first one is the 3D mapping using photogrammetry, structure from motion. And then in parallel on some of the frames that we use, we perform some semantic analysis. So some object extraction, some semantic classification of the data in order to deliver at the end of the day some 3D semantic maps. So some 3D reconstruction with some semantic annotations. Of course, there are different typologies of approaches according to the case. So we can use edge and remote processing. We can use customizer off-the-shelf drones, as we will see in a moment. And we are already working also in an indoor environment, not just in outdoor. And of course, the application itself depends on the goal of the mission that we are delivering. So the two solutions that we envision are the cloud or the edge, or the edge computing. The cloud computing is what as you can imagine, basically we stream the data in another place where we have a big laptop or a big workstation that can process the data in real time. Of course, there are problems on the bandwidth, especially if you have large images, forget to download these images in real time easily, and the latency. There is a delay between the communication. And of course, there is also a cybersecurity aspect. So it's easier to hack basically the drone at the moment. So this is not always a cyber secure from this point of view. And then there is the other typology of processing, that is the edge computing, where the process happens really on board. And here large companies like Intel, Nvidia, or Google are already delivering some nice solution that can be also embedded on drones. So I will briefly give you an overview of 3 projects that have been concluded or are still going on in our groups. The first 2 are Inacus and Auver, where we really use some commercial solution in order to deliver real-time data. And another one is Panoptis, where we customize and we have some edge device that really process the data on board. In all the 3 cases, in any case, we have a real-time processing, and we deliver both geometric information, so really maps of the area, georeference map, and some classification or object detection, as you will see in a moment. Looking at the first typology of project where we use a really commercial solution, we typically use small drones like the DJI drones, and basically we customize an app in order to be able to stream the data on a laptop on the ground. Of course, on this laptop, we also deliver and realize our own app for flight planning in order to be able to plan the flight and communicate in this way with the drone. So the mission starts with the flight planning. Through the app, we give this information to the drone take off, and then during the flight, stream videos or images that are processed in real time on the laptop itself. For Inacus, the aim was to do some real-time mapping for search and rescue applications. So the idea was really to say, okay, we have to be fast to know where are the destroyed buildings in a certain area, and to deliver a map for the first responder in order to prioritize their action on the field. Of course, the problem was to be real time, to do that automatically, and to have a solution that was relatively cheap in order to be replicable also for different groups and different teams of first responder. And of course, when you talk about emergency, you don't have a GNSS or internet connection, so we needed to have a sort of local solution that was able to run on the field, so really locally, without streaming the data to external cloud or servers. And the solution we got basically was to have the streaming, as I discussed before, of the data in a shared folder on the laptop. And from this folder, basically, we had the 2 processes, like I mentioned before. One was an incremental modified version of CallMap, that is a library that you can find open online, a sort of incremental structure from motion that was basically built in the map in real time. And in parallel, few frames were selected to run a CNN network and detect the debris on the destroyed area. These information were merged together into a sort of quick orthophoto that was delivered on the laptop. And this information was also, as you can imagine, was easily georeferenced and then embedded on a Google Earth visualization in order really to give the context also of the information that was acquired. A second example is given by another project that is our. In this case, we were working with the national police here in the Netherlands, and the idea was to basically detect number plates of cars in some remote places of the country. We basically improve and build on the previous experience. Again, the framework was always the same for the streaming, but in this case, basically the idea was to have a real-time mapping using a different approach to detect basically the car visible in this area, and then to have a replan of a second flight in order to position the drone on the back or on the front of the car in order to acquire a second set of images on the car itself and detect in this way the number plate of the cars. So we were basically doing on the flight a first flight to have an overview of the area, and then a second flight in order to just detect the object of interest, so the cars, and specifically the number plates on these cars. So the approach here was basically to use a different algorithm that is given by Islam. So this is something that really comes from robotics, modified using the GNSS information, and basically we were able. Now the animation is not working in this presentation. I don't know why. This morning we have problems with, but in any case, the map was really built on the flight. So the added value of this was that we were really able to generate the orthophoto basically during the flight itself. And at the end of the flight, we were also able to locate basically the position of the images, to do the replanning of the second flight, and then to acquire the position of the cars in the images, and with a cascade of different approaches, always using artificial intelligence, we were able, and OCR algorithm, we were able to extract the number plates of these cars, as you can see in this image. Of course, this process was not perfect. You can see that in some cases, when you have a tractor or other typologies of vehicles in the area, still the algorithm is not able to cope with this specific situation. The last project I will show you today is Panoptis, where basically we're using a different typology of drone. It's an hybrid drone. So basically it's a drone that can take off and land vertically, but then when it is flying in the air, can be basically fly like a fixed wing. So it can cover really large areas. And this drone was used for highway monitoring. So the idea was to monitor the position of the cars over an highway, and to detect possible accident or other anomalies on the lane. In this case, we had a larger drone, so the possibility was really to use an onboard processor. So this NVIDIA Jetson, that is a small, basically PC, about 100 grams, that can be hosted on board, in order to do the process on board, and just with a 4G connection stream the useful information on the ground. In this way, we were making basically all the process not on board, so not we were not relying too much on a good and fast connection with the ground. So in this way, we were really able to fly several kilometers far from the drone itself. What happened in this case is that basically we had a workflow that is represented here in this scheme, where basically we were detecting cars on the lane for every new frame that was coming, and then after detecting this, we were tracking in the following frames the position of this car, in order to infer in the last step the speed of the car itself. Again, I know that in hyperspectral maybe is not very common, but in our case we are massively using deep learning for our application. And in this case, we were really using a so-called multitask network that basically is trained using two different tasks in the car detection and the semantic segmentation. Why we use this approach? Because typically using a multitask approach, we can improve the single tasks. So the use of parallel tasks helps to improve the performances of the single tasks. This is basically what we were using in order to have also, with using just a small data set, good results in the car detection. And basically, we are in the Netherlands, so it was not always easy to fly close to a highway, or at least you have to take a lot of permission. So to test and validate the method, we were using bikes and students with some information about their speed. So basically, we were using for the validation of this method these bikes, estimating what was the estimated speed that we had on the drone and the speed of the bike that was known, because these students were basically tracking their speed, and the results were relatively good because our approach was able basically to estimate more the speed and track the speed in more than about 5-10 frames per second. So quite good, because it was a very high frame rate, having an average error of about 1 kilometer per hour. Again, we have to extend this on the highway, so the cars are going faster. So probably this error was much higher, but still it is quite a good result that shows that also if with this small onboard unit, we can still go online and still be accurate enough in order to detect the results. Of course, this is an overview, but there are still a lot of challenges that I will briefly mention in the following. The first one is that when you use deep learning has still a lot of problems on the transferability. So when you train your data set on a specific environment, it is very difficult that it works also in a different environment. So to give you an example, with earthquakes, if you train the network to work and to detect building damages on an earthquake in Asia, it is very difficult that it will be able to detect the same damages in an earthquake in Italy, because the buildings are built in a different way and they look completely different. And I guess that this is still even more valid for your application on environmental contexts, where really the variability is much higher. So every time you need, when you have this algorithm, to fine tune them in order to get good results. So this is for sure a first problem. The second one is that when you go to online, you need to customize your network, your algorithm, in order to work in this way. So I mentioned before that we use incremental structure from motion SLAM algorithm that comes from robotic for the 3D reconstruction. But on the other hand, also for the CNN itself, or the machine and the deep learning algorithm, we need really to be careful to customize them in order to be hosted on this and to be able to deliver results in real time. And the last but not least, talking about 3D reconstruction, do not expect that the real-time algorithm at the moment are able to deliver the results that you can get with dense image matching or traditional photogrammetric approaches. So still, this kind of application in real time can deliver good results if you need to be fast. But again, be fast is not always the priority. So if you want to get a very good 3D reconstruction, I still strongly recommend the traditional photogrammetric approaches. So I would like to thank my the group of PhD and postdoc who are supporting this work. And yeah, this was a very brief overview of my presentation. If you have a question, I'm very happy to answer. Thank you.
Okay. First of all, I'd like to thank the organizers for inviting me here today, and thank you all for coming today. So when I got asked to do a talk for you all, I decided to kind of take a little bit of a temporal approach to this and look at kind of how drones for river monitoring, specifically in my specialization, have evolved over the last 10 or so years. And the reason I did this was that kind of my career as a PhD student and now my career as a professor have kind of paralleled the use of drones and structure for motion. And so the way that we're going to look at this today is kind of how it started for me specifically. Then I can talk about a little bit about my research, my current research, and then some kind of considerations from the future, which will parallel some of the stuff that Francesco talked about and some of the stuff that Salvatore talked about as well. So where it all started for me was I started my PhD in 2010. And when I first started my PhD, one of the other professors in the department sent my advisor and I an email saying, hey, you guys might want to check out this link to a Microsoft research talk on a product that they were launching called PhotoSynth at the time. And they had an idea that this would be a really cool kind of virtual photo tourism kind of application, but the back end of it was Bundler, which is the kind of proto SFM algorithm. And when we finished watching the video, we were both kind of like, ooh, this could be game changing. An easy way to get three-dimensional data without the kind of expense and knowledge needed for traditional photogrammetry. And so we had kind of this idea that this could really be a democratizing way to get 3D data. And so we set out to collect some data for demonstration to show that this could be done. And the trick was that UAS hadn't quite taken off yet at that point. And so this was in 2010, was when we collected this original data and continued into 2011. But so the original kind of aerial data that we collected was with a kind of old school UAS, a 2.5 cubic meter helium flake height. So we strapped a camera to that and flew over our site. And this is actually the original point cloud. I dug this out of my archive from our river in Central Texas. And this led to our original article that got published in early 2013. But when we first got this data out, I mean, we got 500,000 data points. This was mind-blowing for us, that we could get this much data density. We were killing LiDAR on data density. We had LiDAR for the same site, and much easier to collect. And so just to give you kind of like the level of detail that we can get now, I reprocessed this data in Agisoft Metashape, and now we can get an order of magnitude better data density. So instead of 500,000 points that we were getting back then, we're getting 5 million data points with the exact same photo set. So this is kind of an illustration of how far we've come. And so drones did start to come on the scene after that. Our first drone was a 3D robotics articopter, and this was a little bit rough. These first systems were not that easy to control, and there was a lot of that. I broke more propellers and landing gear than I care to admit on that first drone when we were first learning how to fly. But after that, DJI started to come onto the scene, and things got much easier. And today we're at a place where we're getting, people ask me how hard it is to fly, and I say I can teach a 6-year-old how to fly in no time. So to just kind of show the growth of, this is for kind of, you think about this as structure for motion, but in parallel with UAS, since again, they're kind of parallel technologies. This is just trying to illustrate kind of the growth over the last 10 years and the way that I tried to illustrate this was kind of cumulative citations from what I like to call the originating articles in structure for motion or earth environmental sciences. And I think what this shows is that the original ideas that many of us had in the early days have really kind of taken hold and really taken off. And so you can see there on the graph how many, I mean, we've got over 5,000 cumulative citations on just these 3 articles. And there's many more articles that we could throw in, and the citation rates would be kind of out up into the sky. So I think we as a community have done a really good job with kind of taking these ideas and running with them. And I think there's more and more to come in the future. So the place where I've been spending most of my time and kind of the how it's going part of the talk is been to look at how to extract bathymetry from UAS data and from structure for motion, and applying that to kind of doing both above water and especially below water fluvial geomorphic change detection. And so this comes from my original paper in 2017, and then a follow-up paper from 2019, where I worked with my colleagues Amy Wadgett and Robin Wilson in the UK, and some published software that makes this kind of easy and open source for anybody to do. So for those of you that aren't familiar with the technique or the process, if we have a clear water environment, and that's one of the key caveats here, not everybody has clear rivers, but in clear water streams and in clear water environments, coastal or lake environments as well, if we can see the bottom, we can generally reconstruct some point cloud data from our structure for motion process underneath the water. But the problem is that that's affected by refraction. So the points that we're getting in our point clouds are too shallow. And so the process that I developed, and there's several other processes out there as well, but the process that I developed looks at kind of a multi-camera correction algorithm to look at all of the point camera combinations in the data set, and applies kind of a simple Snell's law refraction correction to push those uncorrected data down to their kind of true depths underneath the water. And so to illustrate the whole process from start to finish and look at change detection, we're going to look at the River Tean. This is in Western England near the Welsh border. And this is data that my colleague Amy collected. But to kind of give you the background on this site, this is what our section of the river looked like in 2009. So a real elongated meander bend there. And in the summer or the winter of 2014 into 2015, there were some pretty significant floods along this stream. And this is what the data looked like when my colleague Amy collected this in 2016. So we had a pretty good meander cutoff event during those floods. And so the goal was to look at how the river was kind of responding and adjusting to this new cutoff condition. So this is the 2016 orthophotograph from our UAS flights. And then going forward to the 2017 orthophoto, I've highlighted some of the areas of change, and they're kind of in the places we'd expect to see change. So we've got in the upstream section here on that lateral bar, the first arrow there upstream, seeing a little bit of growth on that bar, and then at each meander bend downstream, seeing kind of the stereotypical signals of lateral migration. So point bar extension and cut bank erosion. And so I can go back and forth here real quick, and you can see that we're seeing some pretty significant change at the site. So to give you an idea of the bathymetry product that we were able to collect, this is got a fly through of the 2017 corrected data. And so the river here is a gravel bedded stream with kind of pretty typical riffle pool morphology. And the data that we were able to collect for both years was gridded out to 5 centimeter point spacing. So basically, essentially 5 centimeter point cloud resolution for the entire data set, both above water and below water. So we'll fly through here. The colors on the map here are the cooler colors are shallower and the warmer colors are deeper. And so flying over, you can see there's kind of the first riffle here into a nice shallow pool, a real shallow riffle into a nice pool around this first meander bend. Okay, and now into the middle part, which is the cutoff section, a nice short riffle, the deepest section, the deepest pool right here, another pretty shallow long riffle, and then a series of kind of shallow pools leading out to a nice long riffle / run out the bottom part of our site there. Okay, so if we difference those two data sets, we can get some pretty good maps of change. I used the M3C2 change detection algorithm here. And what we can see, or what I want to show you first, is the data if we didn't have the bathymetry. So if we didn't have the bathymetric corrections, we'd be able to get some data on change, and it's still fairly useful, but it's not showing us the whole picture. But you can see that the greens are deposition and the yellows and reds are erosion. And so there's a fairly complex kind of pattern of erosion and deposition. But you know, the change that I'm showing you here kind of matches what we saw in the orthophoto. We're seeing cut bank erosion, point bar deposition, and kind of migration there, and some vegetation change that you can see on the banks. But again, this is kind of an incomplete picture. And so if we add in the bathymetry, this kind of changes the story pretty dramatically. In that we're not just seeing cut bank erosion, but we're also seeing a pretty good signal of pool infilling here as well. So in most of the pools up or down the stream, we're seeing infilling, so sediment deposition, which is not something we were expecting. With that much erosion on the banks, we were expecting to see pool scouring and wholesale kind of sediment exporting out of this reach, but that's not what we're seeing. And so as we go from upstream to downstream, there's most of the pools, we're seeing infilling, we're seeing some riffle migration. So there's some depth or some erosion right here on this kind of riffle, showing that riffle is kind of migrating. And then my favorite, I think, section was this downstream section where you can actually see the deposition pattern kind of reflects the hydraulics. And you can actually see how the water and the sediment kind of get pushed to the downstream bar, and we're seeing kind of that downstream migration of that downstream point bar, which is pretty cool to see. But to look a little bit closer and potentially look at some interesting mechanics behind some of this change, we're going to look at this upstream meander bed in perspective view. So we're going to be looking from upstream to downstream here. And so if we look at this, the colors here are now just purely elevation. And so you can see the darker colors, the purples and blacks there, are illustrating in 2016 that you had a fairly deep pool there. And if we go forward, the color ramp stays the same, okay? But you can see how much change just in this perspective view and the elevation map that we're seeing. So the point bar is elongating from the left to the right, and then that cut bank is kind of retreating in a similar direction. But you can also see that we're losing a lot of the depth, or a lot of the elevation in that pool that's illustrating that pool infill. So if we look at the map of change, we can see, again, a fairly complex response of both erosion and deposition in the point bar, which is not something that we were really expecting, but this is definitely a complex response. But especially in the channel and on that cut bank, we're seeing kind of the pool infilling in green, the erosion in red and yellow. And I think what's actually happening here, and I think what we can infer from this change detection map, is the mechanics of the change. And so there's kind of the black line illustrating kind of zero change, kind of right along here. And I think what this is actually illustrating is that black line of zero change is actually kind of a rotation point for bank slumping. So rather than during the peak floods, a bank toppling event and transporting out a lot of that material, I think what we're actually seeing here is that this is a bank slump that probably happened on kind of the falling limb of kind of the annual flood hydrographs. So we're actually seeing that erosion is kind of, rather than being transported out, is just kind of slumping down into the channel and filling in that pool. And that's, again, not something we were expecting to see here. We were expecting to see kind of more traditional kind of bank failure and kind of transport of a lot of that material away, and a lot of scouring, not this signal. So it was really interesting to see this. So what are the next steps for my work with bathymetric structure from motion? I'd like to do more and more change detection with this. I think we've got some pretty mature techniques here. I mean, with generally structure for motion, but I think the bathymetric workflows are pretty mature now as well. And so going forward, just trying to do more and more change detection. And I think this is going to be important for looking at how rivers are changing in the face of climate change, but also the example here on the right is an example from a river restoration project that I worked on for my dissertation. And so, monitoring things like restoration projects to see how they're responding to climate change and new situations and new environments. But I think if we go a little bit further with change detection, I think one interesting thing that we could probably do with this data too is start to validate some of our geomorphic and evolution models that exist out there. So kind of trying to look at high resolution change detection and comparing that to things like, the data that we could get from something like a Caesar list flood river evolution model might be interesting to kind of validate. One thing I'm working on right now is kind of post-bathymetric correction flow modeling. So actually using these high resolution data to generate two-dimensional or potentially three-dimensional flow modeling. The high resolution doesn't really play well with 3D CFDs right now, just because of the data density and the processing power needed. But in a two-dimensional flow model, these work fairly well. But trying to get things like spatially variable shear stress, measurements or modeled variables, which can be important for sediment transport modeling and also sediment budgeting. And then I think if we even go beyond the geomorphic aspects of this, trying to get it using these data in high resolution habitat modeling, I think is going to be important moving forward as well. And then I think another thing that I want to do is try to start extending these surveys beyond the short reaches that I've started with. So most of the sites that we've done, or I've done so far, have been less than 1 kilometer. but definitely trying to push this out to multiple kilometers or tens of kilometers, I think is going to be important for the future. But the one caveat with trying to do this over larger and larger areas is that most of the physics-based refraction correction for underwater correction relies on having an accurate water surface, because the way that the results are calculated is based on depth, not elevation. So we need a water surface to be able to calculate depth. And the way that we've been doing it so far has been to digitize the water surface either from the orthophotos or from the point cloud directly, or potentially using kind of sparse measurements from the field. But if we want to push this further out, I'm not that interested in digitizing 10 or 30 kilometers worth of river. I did that for my dissertation and it took me weeks. So I'm not really that interested in sitting in front of a computer for that long, digitizing a water surface. But I think that the one interesting thing here is that there's a possibility of, again, trying to bring the modeling world into this and potentially try to run two-dimensional flow models over the uncorrected data to generate kind of real water surface elevations that we can then pull in as the source for our water surfaces to do our bathymetric corrections. But I think the main challenge with this is, what are the river inputs for essentially a fictional river? Because we're using data that are too shallow, we're going to have to change a lot of things. We can't just use discharge and velocity like we would. Those are potentially going to have to be scaled or cut back in some way. And then also looking at even scaling something as basic as Manning's roughness might have to happen as well. And just to give you an idea of some of the test data that I've been doing, this is a little section of the river team that I just showed you here on the right. And the black line is actually the digitized longitudinal water surface that we used in our article. And then the colored lines in there are a couple of different model runs with variable discharges and variable Manning's roughness. And you can see the pretty stark difference. This is through one of the steeper riffle sections in the river, the stark difference that the model gives us versus our digitized surface. And I tend to actually trust the model more in this case than our digitized water surface. So I think models might have an interesting application, especially if we're trying to extend this out to further and further distances. So where to next in general, I think is an interesting question. And I think there's so many ways that this can go. In the last 10 years for me, seeing the explosion of UAS and structure for motion in just my field of river science, but then, in vegetation monitoring and precision agriculture and soil science, like Birgitta mentioned, there's so many ways that this can go. So I'm just going to try to focus on my little corner of the world here in rivers. And then I want to talk a little bit about some general UAS topics that I see kind of as important for the future as well. So again, I think more and more change detection and monitoring is needed. Again, in the face of climate change and river restoration projects, more monitoring data is never going to hurt. And trying to understand how different rivers are kind of experiencing different climate drivers and different changes in hydrology is going to be important in the future. I think there's a lot of promise that's already been shown, and I think it's just going to continue to explode, is what I like to call image processing derivatives. Things like PIV for surface velocity, image segmentation processes to actually get sediment size maps of river environments. And we've seen some examples of that already, and I think we're going to hear more about those later on, and I think those are just going to continue to grow. Multispectral and hyperspectral and thermal data for things like for vegetation monitoring, for water quality monitoring, I think are going to be important. We're still trying to work out some of the kind of technical aspects of high resolution, hyperspectral and multispectral mapping, and thermal data as well is kind of trying to map big, thermal data over long distances is a challenge right now. And I think more and more data fusion is going to happen. Salvatore talked about this at the beginning, kind of the upscaling and downscaling from satellites down to UAS, doing validation, both directions, doing just kind of more and more data fusion. I think we're just going to get more and more data, better and better data, and a lot more applications, and a lot more things are going to come from that. And Francisco talked about this in the last talk. The buzzword in data science right now is machine learning. And I think that this is something that we need to embrace, but I think it's also something we need to be a little bit skeptical about. Francisco talked about transferability. That's one of my biggest kind of concerns about machine learning applications. And so I think we need to kind of test you know, what's happening a lot is when it's appropriate, when we should be using it, but also when we should not be using it. It's not a cure-all for a lot of things. It's got a lot of applications, but I think we just need to kind of be a little bit more, I don't want to say judgmental, but a little bit more kind of discerning about when we're using it, when we're not using it. And then in the river science world, I think that a lot of the data that we're collecting, especially when you get a change detection and the image processing derivatives, is getting us more towards what I've been trying to advocate, and a lot of my colleagues in remote sensing rivers community have been advocating for, is the idea of trying to map kind of whole riverscapes. And so this is longer surveys, combining geomorphology and ecology to really try to capture the complexity that exists in these river systems. So the geomorphic complexity, the ecological complexity, and trying to come up with maps and ways to detect change and look at these systems in a lot more detail than we ever have been in the past. And so I think that's going to be important in the future as well. And then from a general UAS perspective, we're going to go through these kind of individually. Drones have a very strong chance to do a lot of good science communication. A lot of us are kind of accustomed to collecting data with our drones, but if we turn our cameras up and just take some nice videos, they can actually be very, very effective science communication tools as well. And I'll tell you, the drone videos that I've shot with most of my sites have gotten way more attention and traction from especially general audiences, but even politicians and funders, because this is something that they can connect with a lot more easily than the fancy 3D data and fly-throughs that we find so kind of engrossing. But, and so this is just an example here of an estuary restoration project that I worked with a colleague on in the state of Washington. We collected 3D data to try to do change detection here, and she's still working on that. But we decided to collect these videos, and these were actually shown to the governor of the state as a way to kind of highlight how this estuary restoration project is going. He was really excited. It kind of didn't explode on social media. It wasn't viral. It didn't go viral. It's the state of Washington Fish and Wildlife social media accounts, but it got a lot of traction from the public because it was something that people could see and kind of connect with a lot better. So I think this is something that we as scientists probably need to do a little bit more of with our drones, is taking a minute to think about the science communication aspects of this as well. I'm a big kind of proponent of accuracy and precision reporting. And I think this has kind of come up a little bit already, and I think we'll probably hear more about it as well. But I think one of the things that we as a community need to kind of commit to doing a better job of is being a little bit more consistent about how we report our accuracy and precision metrics in our data. Most people are using single metric accuracy assessment or accuracy statistics, so like RMSE or mean squared error. Those are fine, but I think we can do better. There's a lot of different statistics out there, even just basic statistics like the actual mean, the standard deviation, RMSE, min-max. These are easy to calculate from our data, and I think it's beneficial to us as a science community to actually be more forthcoming with these accuracy metrics so that other people can have a better kind of idea of the accuracy of our data, and we're being more truthful, if I want to be honest, with our data reporting. Single metrics are fine, but I think we can do better. And then I'm a geographer, so maps are kind of near and dear to my heart. And I think we also need to kind of embrace spatial representations of error in our data sets as well. These are complex, high resolution data sets. And even when we start to get into kind of better accuracy reporting in a table of statistics, it doesn't fully kind of embrace or represent or the full kind of gamut of error that we're seeing in our data set. So I think trying to embrace spatial representations of error in addition to the statistical, I think is going to be important moving forward as well. And I think this especially comes into its own when we start talking about change detection studies and looking at how things are changing, when we start looking at things like limits of detection or propagation of error through our data sets. The more truthful and the more forthcoming we are, the easier it is for reviewers. And that's where I'm coming from on this mainly. Easier for reviewers and our readers to kind of judge how good the data are for their kind of intended purpose. Precision positioning is coming online very, very quickly. Lower cost RTK and PPK GNSS capabilities are out there. There's even aftermarket kind of add-on kits for a lot of the drones that we already have. And these are going to give us better positional accuracy, especially in our structure for motion 3D workflows, giving us an easier kind of path towards direct georeferencing workflows. But on the topic of the previous slide, this doesn't necessarily exempt us from doing some field work and doing independent accuracy assessments, because just because we have good positional accuracy in the air, that doesn't always translate to excellent positional accuracy on the ground. So still doing kind of traditional independent accuracy assessments is going to be important. But this is going to allow us to cover larger areas and then precise data in harder to access areas. So especially like Francesco said, like in disaster zones, or God forbid war zones, you know, having access to better precision positioning is going to be important moving forward. And the last thing I want to kind of end with is a call to open source methods. I'm a methodologist in my heart. I try to develop good open source methods for a lot of different applications, but I see a lot of articles and a lot of methods out there that don't come with instructions, at least good explicit instructions. And those methods, to me, specifically, even as an expert, but especially to kind of practitioners out in the field, those methods are essentially useless. Those new methods are useless without really explicit written instructions and workflows. And so I think what I'd like to call on you all and as a general kind of science audience to do is, if you're working on new methods, is you really should be working on in-depth instructions and workflows to publish either with your publications or alongside your publications. You know, and you can think about these as being for your students and other people's students, but like I said, I think even more importantly for professionals out in the field that need these new methods to do better data collection and more data collection, it's important. You know, these can be written or video tutorials, both are fairly easy to produce. And even there's starting to be some kind of academic publishing outlets for these methods type articles as well. So that'll be interesting to see how that progresses in the future. And then on the same topic, if you're using any kind of software or code, I think that you really need to make those available in an easy to use format. Okay? No, you know, they need to be as easy to use as possible. You know, and there's multiple platforms for code sharing out there. I use GitHub, but there's lots of others. And the nice thing about these is that there's tools now that you can actually make your software and code easily citable. So you can track your citations fairly easily. It makes it easier for other people to find your code as well. So with that, I'll thank you very much for listening. And if we have time for questions, we'll take some questions.
Thank you very much. It was really great to see how many things we have to take care of that we would like to say bring valuable research with drones. So since we have a bit delayed on the schedule, so I would recommend to ask James in the coffee break outside, and maybe we can start around 11:35, just to make coffee break a bit shorter, to keep the track, because then not to lose too much time. So in 11:35, we will start with the next block. Thank you, everyone.
Thank you very much. Can you see my presentation? Can you see it?
Yes, sure, clear.
Okay. Thanks. So I would start with presenting our work within the work group 2, which is a group on vegetation, and we are dealing with the natural vegetation part, and then Antonino will continue with the agriculture vegetation. So it's not my work only. There are many co-authors. I didn't list all of us, but there's a large group within the work package that was working on many of the issues. And so we would like to know, okay, how can we use drones to assess natural vegetation? So what did we learn actually? I hope you can see it all, because I see. Anyway, how how can we assess vegetation or heterogeneity of ecosystems and complexity of vegetation using drones? There are many different ways and many parameters we can assess, and we try to make a sort of like a compilation of the most important parameters, being like plant composition, plant structure, and plant status, and the dynamics. And we try to make some kind of common procedure or categorization of the framework on how to use drones for assessing different components of vegetation heterogeneity and different parameters like biodiversity, volume, biomass complexity, phenology, stress levels. So it really depends on what kind of parameters we want to assess, and as well on how the phenomenon is distinct and or conspicuous. So we created this giant or diagram on published in Ecological Indicators last year, where we try to summarize all the different information. But if we look at it in detail, we also summarize this in the book that is being edited and published soon, summarizing all the information from our cost action. And within the chapter 5, we worked on this current state and perspectives of vegetation assessment. This is just a summary of the chapter, where we address different parts as methods and examples of best practices and challenges. So now back to the diagram or the framework. If we look at the composition, I just briefly introduced the concepts for the composition. We definitely have to consider a similarity of surroundings. So, I mean, a similarity of the species you want to distinguish. So how much, if they are highly similar, then we probably need some higher, more complex survey design, more complex processing, such as like hyperspectral data, for example, or high spectral data, or higher temporal resolution. In case they are not very similar to the surrounding, then we can work in a more like easy way, because if the species is very distinct from its surrounding, then it is much easier to distinguish and to map or to detect. And then we choose algorithms, or either object or pixel based, depending on the characteristic of the species, or if it makes some distinct objects, or if it's just a spectrally distinct. On the right side, you see some examples of like this for the alien species giant hawkweed, Heracleum mantegatianum, that you might know. It's a very big plant with white inflorescences that are very much easy visible from the distance. So there are examples of different data sources, such as drone data, satellite imagery, where you can, with a different detail, distinguish the plant. And then on the bottom is the example of different segmentation processes. As you can see, that the plant is very distinct from making very distinct objects. So the object classification comes in place. And this is just a comparison of using some open source software and commercial ecognition software. So it's from yellow commercial ecognition to blue Orfeo, and red is the Orfeo also, but random forest classification. This is another example of using deep learning classification of seagrass on Dutch coast from Sander Mucher, who was a co-author of the chapter. So this is to illustrate that choosing the right algorithms and processing workflow, it depending on the characteristic of the species. This is another example of using temporal aspect, where in the deciduous forest, the different species of trees are differently distinct in different parts of the year. So they can be very easily to distinguish spectrally in the time of the spring, but during the summer it can be very difficult. Like you see on the survey 7 from the spring and survey 8 from the summer, and different species are marked with the different colors. So like white is let's see that one is common ash, for example. Considering the structure, it really much depends on how sparse or dense is the vegetation. If it is sparse, then we have much more choice, as illustrated in the uppermost example, where the vegetation is quite sparse, and there we can use passive sensors like optical photogrammetry to get the structure for motion. I'm sorry, structure for motion derived digital elevation model, digital terrain model, and we can from there derive the height of the vegetation and to see this or classify the structure, that see how complex is the structure. If we have a dense vegetation, like on the bottom part, can be much more challenging if for example, the forest vegetation is too dense, or it can be also the grasses. If it's too dense, then we need active sensors to get meaningful information out of the data. Or we can sometimes like combine the two, having the photogrammetry derived information about the canopy and laser scanning derived information about the terrain, about the ground. These are another examples of assessing the structure as constructing the tree from the photogrammetry from structure for motion, this is an example of from Austria, where there was an art installation of forest in the former stadium, and this is the assessment of the forest that was artificially constructed in the stadium. Just an interesting art option of using using UAV for the art. And then if we look at the plant status, such as physiological or phenological status, it really much depends on how symptomatic or how conspicuous is the factor that we want to assess. In case it's not very symptomatic or not very conspicuous, we have to use some higher resolution, like hyperspectral thermal or higher temporal resolution. And we need more complex model compared to the easy to distinguish phenological stages or physiological status. Here's one example combining the status with the dynamics and structure, where this is a monitoring of withdraw damage done by Martin Mokros. I forgot the citation here, I'm sorry. It's also from the book chapter, and you can see the comparison of LiDAR derived laser laser scanning derived digital terrain model and drone derived digital terrain model on the left and right on the upper row. And then on the lower row, you can see the image and then the damage, the wind throw damage in red is the using a combination of the laser scanning and photogrammetry derived drone information. And on the right, you see with the yellow mark the only solely derived from the drones without using any laser scanning. And you can see that because in this case the difference between the canopy level or between the ground of the damaged and the canopy or the forest height was very different, very high. So it's easy to distinguish also only solely derived from the drones, and we don't need the laser scanning in this case. Of course, if there would be very small holes or very subtle differences, then probably the sensitivity would be much lower. So that was shortly about the concept. Then there are different tools we can use to process UAV data. There is also important to consider open source perspective, using free tools, really like trying to promote open source and to build up on the that is preparing new, adapting the algorithms and preparing new tools for very quickly compared to the commercial software. And the last thing would be challenges and perspectives, where during our work we talked a lot about the challenges and about the future perspectives of the tool related to the natural vegetation. And we also carried out the questionnaire to understand the topics that are important for the users of drones. And we can say that there are many technical issues that are like common to all drone applications probably. And these are like, for example, geometric or radiometric distortions, like sensors that are not good enough, or original techniques, or power of processing algorithms, accuracy assessment is a good big challenge. These are expected to be addressed with technological advancement. The advancement of drones is very fast, and so we can expect that many of those issues will be solved, almost solved, or very much done with the development of the technical like sensors or the platforms. Still, we have to consider that imprecision in the data can also always be larger than the subtle changes we would like to detect in natural vegetation, or with larger than the some parts of heterogeneity of vegetation that we are interested in. So maybe we still will have always a challenge in like matching the imprecision of the data with the phenomenon that we would like to detect, and there will always be some kind of mismatch between the two, and we always have to consider what the power of the drone technology is and what are the possibilities, because it's quite often a challenge that communicating the science, communicating our results to the users, that we are sort of promising too much, and then in reality it's not as it seems. So and also it seems for users, it sometimes seems it's very easy, and then when they get into it and see how the complexity of the issues, they are terrified and then run out of away from the technology, which is a shame. But there are also many conceptual challenges, and really we have to bear in mind that the perspectives that the drone offer us addressing this different ecosystem properties is very different from the perspectives that is provided by satellites or the data.
Excuse me, Anna, you have like 1 more minute.
Okay, sorry, yeah, I'm finishing, yeah. So this is not enough to just mirror the procedures that we already use. We have to make a new strategies that would leverage on the drone data. And we really need a standardized workflow for the drone assisted ecosystem studies, as we try to do in our published work and in the book chapter. And we have to bear in mind that drones are really capable to sort of expand portfolio of addressed issues like vegetation types, environmental problems, research questions. And so with the advancement of the technology, we also have to modify our concepts and paradigms in vegetation science, which is the real challenge. And this is what is complex and problem for us now. So we had a very nice time during the cost action with our members, and it was really enjoyed. And I would like to thank all of the people that were active and were working within our group and within the cost action. It was really nice. And it's a shame it's the end, and it's a shame that we had the COVID like disrupting our activities. But anyway, we succeeded to provide at least to finish some of the parts but we still have some more to finish. So there are still some ongoing projects that are not completely finished or published yet, and going to be published soon. Thank you for your attention. That's all from me. Thanks.
Thank you, Jana. And next presenter is Eyal Bendor.
So, good morning, everybody. I'm happen to be into a conference at the same time, so I will give this presentation from the Wi-Fi, and the presentation has to be actually provided after all working group leaders will summarize their activity, but I'm actually working group leader of number 5, which is summarize of all the activity that have been done with Harmonize project. And this is just to state what is Harmonize all about. We all know this. So it's about environmental monitoring using UAS. And as you see, we have lots of publication came out from the project. And still there are some publications on the pipeline. And this is a very fruitful, I think, project where we see all this presentation and also the publication. And one important thing about the Harmonize is that the project could emerge more activities, more projects. And this is something that we need to take into consideration. I just see here some new examples, so not new examples, some examples that were taken under the Harmonize project. Is one the joint project of the aqueducts, and this is in the left-hand side you see the partners, And also we have a project with Italy, Israel, soil spectroscopy for the southern part of Italy. And in this sense, we have also last year we had NASA flight over South Italia as part of the other project as well. So we just finished last week another project that is actually another campaign that is part of 3 projects in one campaign. It was in southern Italy. So these are the people who were participated in this campaign. And I just want to let you know or to ask you if there are more projects that I don't aware of or we are not still mentioned this, please let me know about them and we will summarize them in the final report. Now, I think the main goal of the Water Group 5 is the book. It's a good summary of all activities that have been done with the consortium. So, as everybody knows, it's a Xavier publisher, and myself and Salvatore are editing the book, and the chapters are already in, let's say, in a very, very progress at the moment. I will give some highlight on that in a few moments. And this is a very nice summary of the harmonized activity. So the purpose of the book is to provide an overview of what is actually done within the project, of course. And the book includes a guideline, technical advice, practical experience to support practicalness and scientists to raise efficiency of monitoring. And there are some new examples and very nice examples in each of the chapters. I just want to let you have one sentence from the preface of the book. So we wrote, the editors, just as the cellular phone changed the world communication, UAS drone technology has changed the remote sensing discipline. I think this is the basic thing within all the UAS activity and technology. We are now, everybody has drone. Everybody can see from above what he wants to see, if it is regulated or it is not. Anyway, this is a very, very revolutioning of the remote sensing activity. So at the moment, all chapters went through an external review. 3 chapters are still under corrections. All chapters are going now under internal review by the editors and might be sent back to authors for additional correction. There are some chapters that already went through the external review, but needs some, let's say, some fine tuning of the paper, of the chapters. So don't be disappointed if you get the chapter again, but it's only a few corrections. Please do it, and I'll give you the timeline in a moment. So this is what we had, the timeline. We kicked off the meeting in July 2020, but now we are in almost 2022. And there were some dates within the chapter, within the book activity. But at the moment, what is more important is that we are now expecting to have all chapters ready, meaning that we will need the internal review correction by the end of May, or even less, the end of April, and we will need to submit all chapters after all editing in June 2022 to the Elsevier editor board. So we started with 13 chapters, and actually we ended with 20 chapters at the moment. And the 12 chapters are as following. So we had some reshuffling of the chapters after the submitting of the chapters by the leaders, by the authors, the co-authors. So chapter 1 will be the introduction to recent advance of US technology. This is from the editors. In chapter 3, it will be summarized working group number 1. Chapter 4 will be summarized also some activity of working group number 1. 5, we heard Jana is speaking about working group 2 of vegetation assessment. Chapter 6, this is again working group number 2 in monitoring agriculture ecosystem. Chapter 7, mapping soil property using UAS-based environmental, it is working group number 3. And the same is about chapter 8, soil moisture content, working group number 3. And chapter 9 is working group number 4, is about geometric correction stabilization of images collected by UAV for river monitoring. Chapter 10 will be river flow monitoring. Again, will be by working group 4. And chapter 11 will be again by working group number 4. And the chapter 12 will be some tool and database for use UAS application. The end will be appendix, and we will ask you for each author of each chapter to provide us information about the appendix. This will be brought back by the fine-tuning of your chapter reviewing. So just to mention, we still need 3 chapters to be edited. It's, I think, Laszlo, it's Giuseppe, and it is also Rodan. So please submit your chapters after the reviewing and correction the chapters to us as soon as possible, since we need to review it by ourselves also. So there are this is the number of the chapters. We wanted also to give some video lectures about each of the chapters, and we will do so shortly. Just to let you know something about Elsevier, everybody can enter the Elsevier website and see the chapter and follow the chapter editing, and all the chapters are there. So you are welcome to go there. So you have to just browse the internet, and this is the link for the Elsevier editing GUI. And this is how it looks like. So after receiving the chapters, we will submit this to EMSS Elsevier system that will be processed the book into a final format. And this is just to log in. I will not go through. I skip it. And this is just summarize an Excel sheet. What is the status of each of the chapters, and also we count the words of each chapters, because in the end we need to have certain amount of words together. So we are now in a very good position. So we have about 11. We need to have in the end 120,000 words, and we are in a very good position. As you see, we have total a little bit less, so no problem even with the long chapters. We have some short chapters, but this is okay. Now we are thinking about cover. If anybody has any suggestion, that will be the time, I mean, not now, but will be the time in a few weeks to provide us some suggestion from you, and we will consider them as the cover of the book. I would like to thank everybody for listening to me, and if there are some questions, you can ask me now, or later on you can ask Salvatore, because Salvatore is very aware and very updated with the book process. Thank you very much.
Thank you, Eyal.
Hello, good morning. Good morning to everyone. Okay, I'm Antonino Maltese. I'm working group leader of the working group 2 on vegetation status. We are almost at the end of the cost action. Thus, I would like a bit to summarize what our working group has done, is carrying out during these years. The working group is a quite big one with several members. It was led by me, by Yana Mulerova, that had the first speech of this slot of presentation, and also from Felix Frances. Felix organized the first harmonious meeting. It was the kickoff meeting that taken place in Valencia in 2018. And Jana organized a meeting, a general meeting, general assembly in at the university in Czech Republic. During the period of this period of COVID, we were not able to organize other meetings in presence. We tried to do something also online with a meeting online in June 2020. Also during the period, we had some field data campaigns. The first field campaign was organized in March 2019 in a facility that is in Sicily, close to my university. And the second campaign was always in the same year, in July. During these years of activity, we had also some short time scientific missions. The first was from Jasper Svensgaard from Copenhagen University. He was hosted at the University of Palermo between September and October 2018. And then George Petropoulos, at that time he was at the Hellenic Agriculture Organization and the Technical University of Crete. And it was hosted in February 2020. With George in particular, we published the first work on exploring UAV with the simplified triangle method for soil water content and evaporative fraction retrievals. It was published in the data we acquired in the orchard in Sicily. And this publication highlights the strong connections that are between the working group 2 and that is on vegetation monitoring, and the other working group on soil moisture monitoring. Also, recently, again, George Petropoulos is at the virtual mobility grant. Is a different kind of collaboration. In the meantime, George moved to Athens, to another university, and again on the same data set in order to publish an evolution of the first method. And we will have a presentation from George later on that will explain in more details how to retrieve soil water content evaporative fraction using a full, not simplified version of the method. Okay. As a working group, we participated to 2 chapters of the harmonious book that Eyal Bendor and Salvatore Manfreda are editing. The first chapter is the one led by Anna. We had some content of the chapters during a presentation. And the chapter 6 is led by Casper Johansen. Is especially designed for analyzing the monitoring via UAS of agricultural ecosystems. Chapter 6 is quite complex. Together, also not only Casper Johansen, but also Matthew McCabe and myself are editing this chapter. We have different topics within the chapter: the application in precision agriculture, the map functioning and performance, the mapping of tree crop structure condition, biomass and yield mapping, and as well as irrigation and evaporation monitoring and mapping. And we presented some case studies. Particular first case studies was from the group of Matthew and Casper, and is on multispectral use based mapping of the tree crop structure and condition. The second case study is from the same data set, the one of orange tangerine trees in Sicily. And we tried to give some demonstration on how to map vegetation stress on this kind of vegetation. So the facility was the citrus orchard that was equipped with the radio covariance that provided the energy balance component, or the energy balance component, I mean net radiation, grounded flux, sensible and latent heat flux with half an hour frequency. Moreover, the citrus orchard was also equipped with drill and drop probes to have profiles of soil moisture at different depths. And we carried out some acquisition at noon, not only at noon actually, but also at sunrise, at sunset. The one we presented here with this chapter are the one at noon, using an octocopter equipped with an hyperspectral camera, and also another drone from Salvatore Manfreda that was equipped with a thermal camera. So data were processed in order to show how to monitor soil moisture, as well as evaporative fraction. That is one of the main indicators of the latent heat flux that take place within the vegetation. And it uses both the data from the reflective and the emissive part of the spectrum. It's not the aim of this presentation to explain how the method works, but we are able to clearly distinguish within the field different level of moisture at surface, and I mean with that surface, with the soil, with the rot zone of the vegetation, where the vegetation occurs, and very the skin part of the soil, where there is only bare soil, as well as the evaporative fraction, that is the percentage of energy that is used by the vegetation for making latent heat flux. So the validation was carried out using the data from the flux tower that works on the eddy covariance principle. And in particular, it was carried out on the footprint of the at moment of the acquisition. That is the place where all the fluxes origin. So the flux tower is this one. Actually, this is quite a small version. Is on a tripod, but the tripod is equipped with all the sensors we need: radiometer, infrared gas analyzer, 3D sonic anemometers, as well as soil heat fluxes plates. So also the thermal and multispectral images were acquired by drones during the campaign, and these are some results. Here we can see a map of the evaporative fraction, are clearly distinguishable the behavior of the vegetation, and that have a quite high amount of evaporative fraction, meaning that most of the energy is using for evaporation and transpiration processes, mostly for transpiration processes, of course, but also low values where we have the bare soil. So in this slide, we show also the footprint that at the moment of the acquisition, and the average value of the footprint, weighted average actually, were compared to the evaporative fraction monitored by the flux tower through all the whole day with half an hour frequency. And here we can see the red dot, that is the average in the footprint compared to the values monitored during the days, represented by the black dots. And the results are good. Actually, the technique is quite mature enough to be employed also in operational context. Of course, the new techniques, the new acquisition methods of UAV opens the way to improvement of the technique. That is what we can try to do, but the methodology is quite mature to be published in a book. I would like to give my special thanks to Laszlo, Brigitta, and Salvatore for organizing the meeting, and I would like also to remind all the Lielenthal that was a friend and the colleagues appreciated the research. He was a member of the working group too, and we lost him during the last year. So this is maybe my last occasion to meet all of you together, and I would like just to give a reminder of Holger as well. So thank you for listening. I'm here if you have any question. Thank you.
Thanks. Can you see my screen? Yes, okay. Okay, good morning, everyone. Thanks a lot. My name is Yijian Zhang from University of Twente, the Netherlands. So on behalf of my colleagues listed here, I will present the summary for Working Group 3 on soil moisture state monitoring using UAS. In Working Group 3, there are 4 tasks mainly. So the first one is organizing training schools. The second one is to generate a spectral-based model to evaluate the soil property And the third one is the intercomparison between different survey protocols. The last one is about intercomparison between different instruments, and particularly between ground measurements and aerial surveys. So for the first task, in terms of a training school in 2020, just before the pandemic, we were lucky enough to organize it in Villach. So great thanks to Genot and Daria for their great support and organizations. In this training school, we have several topics linked to soil moisture. So the first one is soil moisture dynamics by Paulo Nastar, who introduced the basics for understanding soil moisture dynamics, but also introducing how to measure it and how to model it using soil models. And then the second one is about soil moisture downscaling from satellite products using UAV imageries. And this is covered by me with a contribution from Vodang and Li Jie on the use of a random forest algorithm. And then the last one is about thermal inertia given by Antonino Mates. So all the lecture slides and the content, also the practical, are all freely available on Google Drive. If you are interested to send me, I can send you the link, which is organized actually also by Genot and Dalia. Last year, there are also video lectures organized by Salvatore, and these two are linked to working group 3 activities. The first one is about mapping soil properties for UAS-based environmental monitoring by Paulo again and Nicolas Francos. And the second one is by Rodan Zhuang on soil moisture retrievals from UAS. Just briefly saying, okay, this YouTube links, click and you can watch the video lectures. So for the second task is to generate a spectral-based model to assess the soil property. So to carry out this task, it's necessary to obtain field and the laboratory spectral measurements, but also soil property data. And in this case, the water infiltration rate is used kind of a proxy to indicate the soil surface property. So in this study, with the soil flow instrument developed by Eyal, it is possible to measure the soil surface reflectance while preserving the field condition without disturbing soil surface status. So such field spectral measurement is then compared with the laboratory spectral measurements and then used to develop certain spectral model for predicting water infiltration rate. And as I said, the water infiltration rate is a soil surface dependent property. So for example, if we have a crust on the surface, then the water infiltration rate will be very, very small. And all these are links to soil texture and other type of soil physical properties. So from these two maps, actually it shows that the spectral-based model can be used to map soil properties. In the left, it's actually the in situ measurements, and then you do some interpolation there. As we understand, there are also uncertainties because we cannot get all everywhere sample to do this interpolation. But in any case, I mean, if you look at the spectral-based model and using the hyperspectral imageries from Janos and Brigitte to predict the water infiltration rate, and you can see they are, well, I would say the spatial patterns are quite correlated with each other. So this afternoon, Nicolas will present this work with the details, and there's also another talk relevant to this topic tomorrow afternoon in working group 3 meeting starting at 2 o'clock. Maybe the timing will be adjusted a bit, but Nicolas will present that tomorrow afternoon. So according to the above mentioned works, some brief points as below. The field spectral, let's say, measurement from the soil flow system overperform the traditional laboratory measurement because it preserves the soil surface status without disturbing it. And then the spectral-based model can be used to map soil properties as we see in the previous slides. But furthermore, the field spectral, let's say the field soil spectral library can be used also to correct the lab spectral measurements through building a transfer function. And this Nicholas will present it tomorrow afternoon. Again, it highlights the importance of, let's say, in situ spectral measurements with undisturbed soil samples. Last but not least, if soil properties like soil texture, but also other physical properties like water infiltration rate can be mapped using spectral-based model and UAV imageries, then this soil property map can be further combined with the pedal transfer function to obtain soil hydraulic parameters. For the third task is about intercomparison among different survey protocols, and there are two parts basically. So firstly, one should follow the current practice in UAS-based environmental monitoring, as explained in this published paper. And secondly, for soil moisture mapping, it also needs to consider different soil moisture retrieval algorithms and methods. So for this second point, a chapter on soil moisture monitoring using UAS has been submitted. In this task, for different soil moisture estimation methods were compared. It includes, let's say, thermal inertia method, spectral-based method, trapezoid method, or simplified triangle model, and then the random forest model. So actually, to be more generic, the random forest model belongs to machine learning approach. And for simplified triangle model, tomorrow morning, afternoon in VG3 meeting, George will present his study using this approach. So Antonino also mentioned this study, because there's also a very close link between working group 3 and working group 2 from Antonino's perspective. And then for the machine learning and deep learning part, Laszlo will present his latest study tomorrow afternoon also. And then his talk will be followed by Qianqiang and Li Jie on using an ensemble of optimized machine learning algorithms for predicting the soil moisture at the global scale. So the optimized machine learning algorithm, meaning there's some kind of a hyperparameter tuning strategy to be figured out. And it's just for your information, let's say for machine learning and deep learning, currently there are two virtual mobility grants under the context of working group 3. So this is some from Luodang. It shows that what the sensors acquisition time and what the land surface information needed for each method, and also explain the strengths and the limitation of different methods. So briefly, both thermal inertia method and spectral-based model. These first two methods can be only applied over bare soil or sparsely vegetated areas. And then the temperature vegetation triangle method can be applied over vegetated areas. And the random forest or machine learning approach has advantage to use all available data for predicting soil moisture. In all cases, in situ soil moisture data should be correct for calibration and validation purpose. So the main message from this task is actually that when different soil moisture retrieval models are going to be used, the sensor type and the acquisition time should be well planned based on the theory and also the follow-up processing steps. Okay, the last task in working group 3 is about intercomparison between different instruments. So as shown in this diagram, it is clear that we have multi-scale, multi-platform systems for monitoring soil moisture and other environmental variables. So how to synergize these platforms for consistent soil moisture mapping is quite challenging. The flowchart here shows a trial to link the satellite soil moisture data with UAV imageries. This is using random forest algorithm to downscale satellite soil moisture product from 1 kilometer to 15 centimeter resolution, using the UAV imageries of land surface features including land surface temperature, NDVI, and elevation. The idea is to train the random forest model at a 1 kilometer resolution using these land surface features as predictors. And after the training, the random forest model will then be applied to predict soil moisture at a high resolution using the UAV maps of these land surface features. So this approach has been extended further by Rodan to improve the prediction accuracy. And in terms of evaluating the accuracy of this approach, it is very important to have in situ measurements. So as I understand from this task, we need a few sites to do such intercomparison between or among different instruments. And here I would like to express the special thanks to Nuncio and his team. They provide the Alento catchment as the research bed for VG3 activities. So particularly in this Alento site, there are 20 soil moisture sensors installed at the 2 depths. And there are also metal station and the cosmic ray probe for monitoring soil moisture content at the spatial footprint of hundreds of meters. And during 2018 and 2019, we carry out fieldworks on Alento catchment, and these fieldworks contribute greatly to Working Group 3 outputs and publications. Furthermore, and again, like Eyal mentioned in his talk, last week, there's a Sera River catchment field survey. So again, great thanks to Nuncio and his team for their support and organizations. I think there are about 20 colleagues in the field with I don't know how many drones in the field, perhaps almost about 10 drones and with the different sensors. And in the field, we also take soil core samples, perhaps also the other instrument to measure the land surface features, but also you can see here the infiltrometer is used to measure water infiltration rate, but other sensors are also used to get the land surface features and states. So just briefly to show you that for soil moisture purpose, the protocol as we identified in the previous work, or let's say in previous tasks, were followed to obtain the UAV imageries. So for example, the RGB and the multi-spectral images we obtained during the known to minimize the shadow effects. And for deriving the thermal inertia map, we obtained thermal imageries before sunrise and during the noon. As such, you can get largest land surface temperature difference during the day, which is needed for calculating the thermal inertia. But at the same time, on the ground, we also deploy and distribute spatially soil moisture sensors at the beginning of the campaign in order to capture the spatial temporal dynamics of soil moisture patterns. So we expect that even after Harmony's project, the data obtained in this Sera River campaign will continue contributing to our understanding of UAV-based soil moisture monitoring. So just a brief cap, the main aim of Working Group 3 is to define a shared methodology to understand the spatial temporal dynamics and dynamics of a soil moisture over different scales. And accordingly, the book is already submitted to support this deliverable. And also, as we can see here, just to remind that, let's say, although in Working Group 3, we focus on soil moisture, but soil moisture itself is not isolated variable. It's also linked to dynamic and static features. So considering the time limit, I would say, okay, the soil moisture can be also applied for many purposes. One of them is to calibrate eco-hydrological models spatially, and this can improve the model performance. But then in terms of resolution information, do we use higher resolution or coarse resolution? There's still no conclusive findings. With that, I would like to conclude my slides with an advertisement for tomorrow's VG3 meeting. So I hope I keep it within 15 minutes. Thanks a lot.
Hello, everyone. Oh. I'm trying to share my screen now. Hope you can see it. Could you please write in the chat whether you can see the screen? Thank you.
If you make it to full screen, maybe.
It is full screen.
It's okay.
Okay. I'm very glad that we have this meeting, and unfortunately, whether Matt nor I could join in person, but I'll do my best to present the results of the activities of working group 4 devoted to river monitoring over the course of the action. So I will shortly talk about the main research topics that our working group had, then the meetings that have been organized, the short-term scientific missions, the publications within the activities of the group, and shortly I will talk about the cooperation with working group 1 at the end, which Sorin will probably expand on in his presentation. So the main research topics were, first of all, of course, the best practices of river flow monitoring in general. And in this respect, we have prepared a book chapter that is going to be a part of the book that Eyal has been talking about. The second point have been the comparison of algorithms for image velocimetry. In the course of this activity, we have organized one field campaign in Belgrade in the beginning of the action. Then there have been 2 short-term scientific missions and a paper by Sophie Pierce that has last week received her PhD. So this paper in the recent years have gotten over 40 citations. And this was one of the very interesting comparisons of 5 image velocimetry algorithms. The next research topic has been the monitoring of river channel dynamics. Here, a book chapter has been prepared by Laszlo, which is going to be a part of the book that we'll see World this spring. And then there has been a collective work on data for image velocimetry, where an archive has been prepared with over a dozen data sets for river flow monitoring, together with reference data and data description paper by Matt that has been published in July 2020. The next research topic has been seeding for image velocimetry. We have worked on characterizations of seeding conditions, including seeding distribution. Here, Silvano Del Sasso and Alonso Pizarro has done an amazing job of publishing a series of papers devoted to different aspects of this topic. Next, there was a work on video stabilization. Of course, it's not only characteristic for river flow monitoring or river channel dynamics. There is always a question of how to stabilize the videos acquired with the help of UAS. But we have focused, of course, on the applications for rivers. There has been a short-term scientific mission of this respect. Then there has been the software developed by Robert Lubicic that is now publicly available on GitHub. It's open source, can be used by anyone, has a very intuitive user interface. And there has been a paper published the end of last year comparing different tools and techniques for stabilizing UAS imagery. And last but not least, there has been a book chapter for the book that is going to be published this spring, led by Salvador Peña-Jara, that has been not only covering the topic of stabilization, but also geometric correction, for example, the removal of lens distortions. And the last research topic has been image enhancement. There has been another STSM where actually this March, where Robert has worked on a series of Jupyter notebooks that allow to take pieces of code and play with different techniques of image enhancement, different filtering techniques. And these all will be also published in April online. And this functionality has also been included into the previously developed software for stabilization. So now it's a complete pre-processing suite that allows also to proceed with image enhancement, not only with the stabilization. Here is a little bit information about the image enhancement. There has been information on different image formats and color spaces, how they can be used in pre-processing, what would be the differences. Then there have been 11 filters tested. The 5 images that you see in the middle of the screen are test images, which are in these Jupyter notebooks, which can be processed with all of the described techniques. And there is also an option of filter stacking, namely playing with the order of filters applied to different images. What does, which influence does it make if we use filters in a certain order? And here are a couple of examples of what the results in the Jupyter notebook look like. For example, this is from color spaces, the original image, and if we extract one channel out of the original image, which of the tracers are more or less visible. For example, in the we have seen in here that we have red and blue tracers, and that in different channels, some of the tracers, for example, here are seen much better than. So the red tracers here are seen much better, for example, than if we work with another channel where the blue tracers are much more visible. So sometimes, for example, playing with color spaces can be an efficient technique of extracting seeding information from the imagery without any other filters. The next topic are the meetings. So for working group 4, we have had a total of 6 meetings, 3 of which were a part of bigger assemblies, and 3 have been devoted particularly to the activities of the working group 4. First of all, in Belgrade with the field campaign, there has been a meeting in Rome of working group 4, where we worked on comparison of image velocimetry algorithms. And another meeting, the last meeting from which your picture can be seen on the screen. This was the meeting in 2020 in Austria, where we already worked together on image stabilization algorithms. What concerns STSMs, we have had a total of 8 STSMs for the working group 4. The first 2 have been devoted to the field campaign in Belgrade. Then there has been a meeting on an STSM on image stabilization. The STSM that Laszlo had in Italy has been devoted to the creation of videos to promote cost activities. Then there has been a meeting, STSM on soil erosion. Josie from the UK went to Germany for that. There too, the STSMs number 6 and 7 have taken place in a form of virtual mobility grants. The number 6, it was devoted to image enhancement, and the number 7, it was the creation of an operations manual in cooperation with working group 1, which I will cover in a minute. And the last one on data collection for flow and geomorphology, Martin Jolie from the UK attended Hungary. So the publications, we have had 9 conference contributions over these years, 12 scientific papers, and 4 book chapters. So a total of 25 works have been published, and the full list is available in the appendix to this presentation. I think that we will share presentations on the Harmonious website later, and you will be able to see the whole list if you're interested. So, and the last part is the cooperation with the working group 1. We have worked on the operations manual based on the requirements of European Aviation Safety Agency with the specifics for environmental applications. We have developed a template of an operations manual together with working group 1, an example of concept of operations and an emergency response plan. For example, a part of the operations manual are checklists, as you can see on this screen, and there are many more others, which can be very useful in environmental applications. And this work is going to be published in the near future too for the use of our whole community. So this was all from my side. Thanks a lot for your attention. And if you have any questions, I'm here. So you're welcome to ask them in the chat or yeah, or in person.
Hello, everybody. Thank you very much for being here. And it's a real pleasure to me to be with such a nice audience and to see my colleagues that are online. If I may start with a joke, thank you, Salvatore, that when you started this harmonious, you started working group one in the beginning, of course. And in the end, it's a working group one. So thank you very much for having this chance to not close, but be one of the last that speak about what we did in Harmonious. And it's, for me, for sure, it's not yet. Because from here, we learn a lot, we, like country, we, myself, my group, and for sure we will develop our relationships, and we still have such topics in common, and I'm sure that we will develop later these topics. My name is Sonit Rabban. I come from Polytechnic University of Timișoara, so we are your neighbors. And in the following minutes, I would like to share some information with you. I will not share all the information in my presentation because some of them have already been highlighted in the previous presentation from Salvatore and from Dalia. But working group one, the objective of working group one, it was to identify standard procedure for UAS data. And the deliver code was a guidance and the workflow for automatic geometric and radiometric correction from UAS page images. To fulfill this task, we try to, and also we have some indicators. We have a number of scientific articles producing collaboration, like 3, we have a training course in Reykjavik, we have 8 short time scientific mission, 2 virtual short time scientific mission, we have working group meeting, we have workshop, and 2 book chapters. So to fulfill this task, we try to come together with what we need and what scientific material were present. So one of the first paper, it was on the use of UAS for environmental monitoring. The other one, the second one, it's referred to accuracy of digital surface model derived from optical imagery acquired with UAS system. The third one was current practice in UAS-based environmental monitoring. What I'd like to mention is that all these scientific papers were very well and good, made a good impression in the scientific world. Actually, this one was one of the most scientific paper for months in the field. So it's not about citation, because our desire is not to have the most scientific papers. It's about the impact of the paper. So we have in the beginning, when we look on the task and the objective, we said, oh, it's a very easy one. But when we approach and when we start to dig, we understand that it's not easy. And we have some challenges and difficulties regarding the mass utilization of UAS for environmental studies. And we understood better there is a serious challenge to harmonize and provide standardized guidelines to UAS for different types of studies. And on that time, in the literature, was lack of standardized procedure for georeferencing, for geometrical or geometric correction, for choosing appropriate GSD, image overlap, and so on. The purpose of the scientific material was to provide practical guidelines for environmental studies, underline the interconnection of this step in successful workflow with an emphasis on the type and quality of the final product, depending on the final goal of the study itself. So given the huge number of environmental constraints and specificities, we understand and we pointed that it's almost impossible to build a protocol that can be applied in all the possible conditions. But what we understand and what we promote is that it's possible to provide suggestions about what should be done and what should be avoided in order to improve the overall quality of the final product. And Salvatore mentioned before all the interaction between the indicators, between the sensor, between the platform, software, and atmospheric condition, terrain complexity. It's not easy to build the guidelines, but and all of this we have to keep in attention that we have to target the regulation, use experts by UAS, imposing the operational limitation, taking the administrative procedure for flight permission, pilot licenses, and so on. So we propose a UAS environmental mapping workflow, and in the end, all of this scientific material, because since now I talk about scientific materials, we want to put it in a chapter that can be available not to the just scientific world, to our students, to our readers, and so on. So all this scientific material, we try to implement it in 2 chapter books. Okay, so our job was done in 1 or 2 years. So we ask ourselves, what's next? So we understand that keeping in mind not just people who are doing research, keeping in mind the people who are students, readers, and so on, we built a glossary of UAS, terms developed by Harmonious. This glossary can be found on Harmonious webpage. Together with the working group 4 and 2 very expertise and high quality research ladies, we built an operation manual for EASA. And this is another aspect that we have in mind. So we want to provide information, not just for the reader. We want to provide information, quality information from European agencies. And we think that this is another secondary but very important goal of the harmonious cost action. So with Daria, with Stefana, with Yanis from Cyprus, with Salvatore, we build this operation manual. And those of you who are interested in more discussion and more information, you are invited tomorrow from 9:30 to working group 1. I try to do my presentation very short because another goal of our working group 1 is promote yes, do the partnership between the researcher, between the universities and companies. And I have today, I invited today with me one of my friends and one of the Polytechnic University of Timisoara partners, Bogdan. And I would like to give the floor to Bogdan to share some information with you about what they are doing and how their work can help our studies. So, Bogdan, please.
Things that can be done with drones, and I think we're coming down with the complementary part of actually carrying what you develop and carrying what you're doing and making the whole thing work. I have with me actually our heli, we call it Barry, I think that's why. And this is a K-MAX helicopter. Some of you may be acquainted to this type of helicopter. It's very efficient because normally up to 30% of the power is being lost to that little propeller that is normal helicopters have. Due to this design, the propellers intertwine and all the power is actually used to the payload. And this actually brings us to our project. So our focus with our helicopter variant is has the main purpose to lift as much payload as possible. So I can find the thank you. So there's two really important aspects that we're focusing on. First, payload and length of flight, and sorry. And second, it's a good thing it's not karaoke, it's my voice just failing. Second is the modularity. There's many uses for drones. So some people might need to lift 200 kilograms, some people need to lift, let's say, 10 kilograms, but to be highly maneuverable and to carry them for as long as possible. This is either you can see either as a lift in the future or it's a render of our program. This is what I mean. So our Berry is built to be modular. So in a minute, you can change its use for crop spraying, for example. We're focusing now on the next part of the presentation will be about crop spraying. So from carrying 80 kilograms of payloads and spraying them for 1 hour across your crops, by changing the module, you can go to fire extinguishing. And there you can go to greater heights of fire extinguishing inside rooms that are very high, so you can't reach them with anything else. Then you can go to rescue operations, woods protection, you go to tourism, extreme sports, whatever your imagination can build. These are some technical characteristics of our drones. So we can lift that 69 kilograms we have it here. We built this because when we started, there was a legal regulation that the mass lift-off had to be under 150 kilograms. Now that we proved that it works, we can scale everything and go way above that. So depending on what your needs are, we can accommodate with our Berry. Like I said, it's about, this presentation is mainly about crop spraying. So we have a bit of information about the land that is available for agriculture in the European Union. And now, why somebody would use, and this is just a small example of why you would use drones for crop spraying. And there's one thing that is very known in the agricultural community is that if you need to spray your crops, you waste between 4 and 7% of the crop by spraying it. So those tracks where the machines need to go destroy between 4 and 7% of their crops. Now, some people got wiser at some point and they stopped planting on those technical tracks, but that's actually even worse because you have to make them bigger, larger than the actual footprint of your tire. And again, anything outside that is a plus of minus, so to speak. And 47% does not sound like a lot. However, doing a small exercise for the Romanian market with clear numbers taken from our statistics, main organism, I can't remember the name, but it's, you have it there, INS. So 7% of a 500 hectare field of wheat is 7% is 47,000 euros. Now, thinking that our drone is somewhere around 95,000, two sprays on different grounds, of course, justify why we should go by air and not by the traditional methods. First, here we are presenting the strictly from a price position, which is maybe not the best approach on an academic level. So I'm going to go faster and explain exactly for crop spraying the benefits. So in comparison with electrical drones, I forgot to tell you we are using kerosene, so even our recharge times are a lot faster. So even if in your applications you need to fly, let's say, for 3 hours with 3 kilograms, you can do that. But if you were on batteries, you would have to either change some really big batteries or wait hours for them to recharge. This way, you can recharge them almost instantly, and even the environment is better off because we are using a constant speed, and we are adjusting everything from our pitch control system. So it's even better for the environment than any other solution existing. Of course, when the batteries will be as efficient as we know that they will be at some point, we will go fully electric. I'm going to stop here because all the rest is actually, again, financial and it's not suitable for academic environment. But I don't know if now or when we are ready, my partner is going to start the engine on the main drone, on our big bearing, and you're invited to hear it all. Thank you.
Important information, the lunch break is coming. So on your way, you can pack your stuff and you can go together to the lunch, which is 900 meters away. So we need a short walk. It's nice to get some fresh air out. So then we can just stop by and check the demonstration. It's really amazing. And important that we start at 2:30. So we try to be here on time, like 2 minutes before 2:30 to start the next session. Thank you. Person? Okay. Okay, let's try to start, and then we will say, we will wait for the feedback to the notifications. So, welcome, Gabor. Thank you, Lars.
Maybe it's better like this. So, dear ladies and gentlemen, dear colleagues, thanks for the invitation. My name is Gabor Pop. I'm the manager from Hunger Control. I'm the head of simulation validation unit. Officially, but also I'm a project manager of the Airborne Communications development project. And now I would like to tell you a couple of words about. But first of all, just a slide about Hunger Control. Hunger Control is the Hungarian air navigation service provider. It's one of the leading service providers in Europe, driving the improvement of safety, efficiency, cost effectiveness, and environmental sustainability. Hunger Control is responsible for providing air traffic services in the airspace of Hungary, of course, and since 2014, on a NATO assignment, also in the upper airspace of Kosovo. The main task of our air traffic controllers is, and operation personnel is to ensure the safe and efficient flow of the air traffic in the Hungarian and K4 airspaces, and also at Budapest, Liszt and International Airport. Traffic in Europe has changed significantly due to the COVID-19 pandemic in March 2020. As you can see from the record year in 2019, the air traffic in Hungary fell by 55% in 2020. And there was only a slight increase in number of movements in 2021. According to Eurocontrol, the European Organization for Safety of Air Navigation, there are three scenarios regarding the recovery of European air traffic. The optimistic scenario, shown with green line, says that we will achieve the 2019 level around 2023. The base scenario indicates a slower recovery, while the red line, the pessimistic scenario forecast to reach the record level around 2027 in number of movements. Despite the pandemic, the number of drones in Hungary is forecast to increase, especially in the coming years, according to PricewaterhouseCoopers research made for Eurocontrol in July 2020. According to their analysis, an average of 2.8 compound annual growth rate is expected for the next 10 years. The realistic scenario, which you can see in the picture, says that the number of drones in Hungary will increase from 55,000 to more than 70,000 by the end of this decade. The weight of non-orbit drones is expected to increase from 2% to 10% of the total number of UAVs. This means that Hungarian drone users will buy more complex vehicles instead of purchasing cheap orbit drones. In 2017, the CESAR joint undertaking drafted the use space blueprint, a vision of how to make use space operational possible. The blueprint proposes the implementation of 4 steps, services to support the EU aviation strategy and regulatory framework on drones. On April 23rd, 2021, the European Commission implemented Regulation 664, was published on a regulatory framework for use space that will allow the start of the U2 phase of provision of services with drones within the use space airspaces. The U2 phase stands for services for flight management. This includes initial services for drone operators, such as monitoring, flight planning, flight approval, tracking, geofencing, geocaging, and interfacing with conventional air traffic control, like ground control. The other regulation, the number 665, defines the requirements for air navigation service providers and other air traffic management network functions in the use spaces that are designated in the controlled airspace. This legislation defines 2 functions. One is the CISP, the Common Information Service Provider, and the other one is the USSP, Use Space Service Provider function. Eurocontrol has been responsible for the ATM, the air traffic management, until now. Our top priority is to maintain air safety on the highest level possible, while increasing efficiency in order to save fuel for airspace users, and of course to reduce emissions. We are focusing on expanding our regional free route airspace and optimizing Hungarian sectors such as the freshly reorganized terminal and using area. Our purpose is to control the upper airspace of Kosovo in the future as well and maintain a perfect cooperation with Hungarian defense forces. As a consequence of the new regulations, new tasks have been added next to Hungary Control's previous functions. We call it UTM, the UAV traffic management. Those who live in Hungary and use drones will probably know that the microspace application is the official drone application of Hungary Control, which supports and helps drone users to use their devices safely and legally in accordance with the regulations that came into force on 1st January 2021 in Hungary. Another task is the design and provision of common information service provider functions, previously mentioned CISP function. Since Hungary Control is one and only organization in the country that has all the information regarding the airspaces, regarding all controlled and non-uncontrolled sectors, military airspaces, dangerous airspaces, and of course, we have the information on the real-time air traffic as well. We have to focus also on supporting use-based service providers too, both private and state-owned companies that will support the safe and efficient movement of drones in the use space. And in order to perform these tasks, we need to develop and set up the air communications network, a new infrastructure based on mobile communication technology. And as you can see, our aim is to strengthen the relationship between the two traffic management systems, the ATM and the UTM, in the long term, since our airspace is limited and there will be more and more users in this limited airspace. The aim of the Aircraft Communications Network project is to create a mobile service provider that will cover the entire Hungarian airspace with the help of additional radio network infrastructures and the frequency spectrums allocated for this purpose by using the terrestrial infrastructure of one of the existing mobile operators of Hungary, such as Vodafone, Telecom, or Yettel, which was Telenor Fast. The radio network would allow the communication, detection, and identification of cooperative drones and other airspace users as well, such as small aircraft, gliders, helicopters, paragliders, and hot air balloons, and so on. Drones below 100 meters will communicate using one of the currently available Hungarian mobile network infrastructures. But the air communications network above 100 meters will be operated on a separate frequency range. Our intention is to install new antennas on the existing base stations that will facing to the air. The data connection will be provided on the 5th generation mobile network, 5G, while the GPS, by the GPS and the Galileo systems, you can see in the top of the picture, will be responsible for drone positioning. We think this is the only way to guarantee the separation of UAVs from each other and from other airspace users. And this is the way to ensure the previously mentioned geofencing and geotaging functions to meet these CESAR EU2 requirements. As you can see, obviously, the underground environment, like many other buildings or places, will be protected by this geofencing technology. And once again, this is only for cooperative drones. We cannot deal with non-cooperative drones. That is the business of our military, the Hungarian Defense Forces. And a couple of words about the requirements of the air-ground communications network and the benefits of mobile network technology. Approximately 10 years ago, during the design of this fifth generation mobile technology, 5G, the control of drones and robots were already intended to be one of the main applications. That's why high reliability and cost effectiveness is a must in terms of requirements. On 5G network, the latency is less than 10 milliseconds, which we believe is more than enough. The communications channel is guaranteed, and the mobile networks use a unique 64-bit encryption. There is a standardized technology, so many drone users are already developing for 4G and 5G technology, such as DJI, Unique, or Parrot, and so on. And it is predicted that in the future, all drones will be produced with built-in modems, and that's why it is essential that the energy demand must be optimized to the vehicle. And lastly, interoperability in terms of the communication system. Should we need better coverage in the airspace of Hungary to increase flight safety, or we need higher bandwidth for streaming solutions in the future? It won't be difficult to install a new antenna on a base station and connect it to the existing airline communications network system. Ladies and gentlemen, I would like to thank you for your attention. Should you have any questions, please drop me an email on this email address. Thank you.
Thank you, Gabor. Do we have one short question? If not, then we can move on. You can cover that from coffee. So the next presenter is Eva from the University of Stockholm. We will talk about UAS application in forestry.
Dear ladies and gentlemen, I'm Esa Tidai from the University of Stockholm, Faculty of Forestry, Institute of Geomatics and Civil Engineering. I am, and all the presenters are also forest engineers, so we have a forest background. So that's the main reason that I will talk about the forest monitoring, the application of the UAS in forest monitoring. So the co-authors are former students and colleagues currently. So generally, forest monitoring you can monitor the forest from quality point of view. Recently, more and more health issue is coming in front, and to react to this very quick health issue, UAV can serve as a very good monitoring tool. From quantity point of view, the area of the forests, the area change of the forests, especially the height, and finally the volume of our forests is very, very important. And so we are, let's say, from the traditional photogrammetry background, but we have seen the advancement in image etching techniques very, very much. So semi-global matching and structure promotion algorithms getting more and more powerful in the middle of the 2000s, and there were some other efficient image matching techniques as well, which made available automatic digital surface model creation. And based on those automatic digital surface models, we can create the normalized digital surface model, and of course we can derive the height. So we have some former example on forest stand height. So at that time, we were using coarse resolution images, and that time, so here you can see the digital terrain model. Here you can see the changes of the forest stand height, and here some very nice correlation concerning the surface model derived forest stand height and the field measure forest stand height. So if we go further from the forest stand height, then we can use some these equation to derive the volume of the forests according to this equation. So this is a little bit modified equation, very common in forestry. So you multiply the height, let's say the crown projection area, and the multiplication of these two is the volume between the ground and the top of the ground. And you have to define this four number, which serve as how dense it is filled with wood itself. So this is the basic equation, and according to the automatic creation of this digital surface model, so we did get better and better results, even quantified. So we had this background, and of course we were fond of the UAV, and of course some cheap and very fragile Chinese tries. We have had the chance to get the DJI Matrix 600 Pro. So I don't know, most of you may know this hexapoker. It has a quite nice payload for 2 kilograms, approximately 30 minutes flying time, and it has a redundant system of GPS and dimensional navigation system. So we have Sony Alpha 7R camera, only with a 35mm optics, and additionally Parrot Sequoia multispectral camera. We had some problem to fix the Parrot multispectral camera because the wire were so rigid that the gimbal couldn't move or balance the Parrot Sequoia. So finally, we fixed it on one of the arm of the drone, and that, oops, sorry. So here you can see in a closer look But that resulted that the 4-channel images were nice, but the RGB images, because it's linear readout, so you can see that these supposed to be straight lines, but the vibration goes less. So we use this system to drive the very first playground, let's say the botanical garden of our university. That time we used much higher Fahrenheit than the current Hungarian regulation allows. And we use 2.5 centimeter ground resolution. And generally, we produce the orthophoto mosaic and the digital surface model or normalized digital surface model. So here you can see some nice example. Additionally, we get this DJI Matrix 100 with an RGB camera X3 and a thermal camera XT. Unfortunately, this thermal camera has a very long focal length, so very narrow field of view. It was a kind of mistake, so the equivalent focal length should have been 19 millimeters, not the real one. But with this thermal camera, so forest health issue is very much influenced by games. So the game population in Hungary is quite high. So here you can see on the left thermal image. I'm not sure if it will be. So the small ones are wild boars and the big ones are deers. So it was really amazing to watch such an incident through this thermal camera. And on the right, you can see some, let's say, game damages, not in forested area, but near forest, where the forest management company is responsible for the game management as well. So here, another very current topic in Hungary, the health issues of Norway spruce. So in Hungary, we have, let's say that after the First World War, Hungary lost most of its coniferous stands. So between the two World Wars, a lot of coniferous plantations were created in Hungary. But those coniferous plantations are not on the natural habitat, and recently more and more health issue is coming in front, such as the dying of the Norway spruce. And the dying, so this is situated in southwest Hungary, in Erzsébet, and because it's a mixture stand, so it's very hard to estimate how much tree you have to fell on how much area. So we could use UAV images very effectively to determine the affected trees. In this next example, this is another type of conifers, the spot spine, and it's really interesting because this spot was detected by Sentinel-2 satellite image time series, and then we went out there and we made some UAV multispectral images, and we created some field sample, but it's still ongoing what was the cause of this very short dieback of the Scott spine. So generally here you can see one compartment also in Erzsébet, which is also a mixed forest stand, so one part is already cleared. And here, so this is the digital terrain model, digital surface model, and here you can see the orthophoto and some treetop detection color about the height of the single tree. So, of course, generally, coarser normalized digital surface model was ideal for forest and height estimation, but nowadays with these UAV images, very high resolution normalized digital surface model is suitable for single tree height estimation and measurement. But of course, if you want to determine the forest and height, you have to determine the digital terrain model itself. And now we have an ongoing research on how to define the digital terrain model based on UAV images purely. So here we use Mavic 2. We had some 100 by 100 meter sample sites where we had some reference measurement with terrestrial laser scanning. We had some ground control points, of course, and we defined, so this is very important because the official DJI flight planning software doesn't have this function of the terrain following mode. And if you are flying on a steep terrain, it really doesn't matter that you're planning the overlap on the top or on the bottom, or you split the flight. So this is a very nice feature of drone deploy. So we use this application, and we plan to fly at from 3 different flying height, 80, 100, and 120 meters. And with 3 by 3 different overlaps, so 90% overlap, but if you mix every second, 80 or 70% overlap can be produced. So let's say 90 by 90% overlap was the original, but with mixing out some photo, you can derive 80 or 70% overlap. So of course, 3 by 3 by 3, altogether you have 27 variation. The processing was based on meta shapes of the structure promotion algorithm. Some further point filtering was done in cloud control. So here you can see that the investigated parameter of the result was the point density, the size of the triangle of the triangulated irregular network, and the deviation of the reference. So based upon this, here you can see some deviation. So in this example, we had very good errors or deviations. So from 2 meters to 2.5 meters. So here you can see some results. We created a kind of ranking between those 27 different variation. So the alignment was unsuccessful in 7 cases. And here you can see that the best was the 80 meter flying height and 90-90 overlap. The second was the 100 meter flying height, 90-90 overlap. Then 80 meter, 80-90, 100 meter, 80-90. So 80 is the forward overlap and the 90 is the side overlap. So, and here you can see on the graph the flying time requirement. So here you can see that, of course, 90-90, of course, it takes the longest one, but here you can still find some very good representation which gives you the digital terrain model back. Of course, this kind of investigation is so we should have do it in different forest stand type condition. We just present it here in one, but just to have an overview, so it has some conifers as well. But even in conifers, we could very nicely detect the real digital terrain beneath. And here you can see some profiles. So maybe from Hungarian participants, so this is the DDM5, is the, let's say, official Hungarian digital area model, which has some deviation from this UAV, this digital So further possibilities, of course, we are not very much satisfied with this parasectorial camera. We had a lot of technical and some other issues as well. So we are planning to get some other multispectral or even hyperspectral camera. We are keen on getting an ALS or LiDAR sensor on a UAV. And of course, we are somehow lucky because on not habitat populated area, the Hungarian regulation is better for us than for example, a company who would like to map the towns or the surroundings. But even for us, the regulation is quite complicated. So thanks for your attention.
One short question from the crowd. Okay, if not, then it could be also the coffee break. Okay, so the next presentation will be from online, from Gabor Babot. He seems to be there already. Soon we'll give you the presenter role.
Good afternoon.
Just a minute, Gabor.
Okay. So, good afternoon. Can you hear me now?
Yeah, yes. We can hear you. You can even speak more louder if you can, please. Thank you.
Sorry, I can't understand you well because of the the noise of the room, but I'm trying to understand. Can you see my monitor and my presentation?
Yeah, we can see it. And
okay, thank you.
Put it full screen.
Okay, thank you very much, dear Chairman, dear colleagues. I will present our new method. We are working on it since 2008 because in an information society, it is important to know about the accurate state patterns and trends of the environment. So that's why we started this project. This high-resolution area monitoring system depends on the next principles. We are working with 0.5 centimeter to 5 centimeter spatial resolution. We are choosing 2 square kilometer sample areas by the national parks and government companies, and we are trying to use 800 meter flight altitude, and we need a huge ground speed. I will tell you why. And we are trying to do it with only 55 centimeter root mean square error.
I apologize, Gabor, but your slide is the opening slide. Can you put it full screen, or can you just reshare your screen, please?
Sorry.
Opening slide, it's not moving.
It's very hard to understand you because of the echo. So, can't you see my my presentation, or?
Yeah, not in full screen, and it's not going well.
Sorry, I can't understand you. Okay, so if you can see my presentation, I will. So
it's not visible.
It's not visible. Sorry, and what can I do?
Full screen, maybe the share is not the best.
Okay, I will reshare my screen if it's okay.
Okay, it will be nice. No, it's great. Perfect.
Thank you very much. Okay, thank you. So we are trying to find the best representing spots of the countries. the test sites are in Hungary. Now we are surveying 31 spots till 2018, and these spots needs surveys 4 times a year. And you can see on this picture the potential sample areas of the protected areas of Hungary, but these red spots are the surveyed spots, and you can find some images about these spots. Okay, so why is it important? Because these high-resolution aerial images are useful when we want to find out something on the satellite image we have. And if we have this special scale of remote sensing, this special level of remote sensing year by year, we can find these spots, and we can find that what we can see on the satellite image, so we can calibrate in the past. And it can be very important because we can't walk on the sites on the past, but we can see into the forest and we can see into the marshes. So this calibration capacity is one main point. And the other one, we can make multispectral images in a new level, and we can make a monitoring system in the new level. So it's important to find this 1 or 2 square kilometer areas with other companies together. Okay, so at first we have to choose the areas, and the next is the flight. We use UAVs and manned aircraft too, and we use these spots to determine, to find answers for the field researchers. We have tested our method in the field, so we could find the limitations of our method. Now you can see the Haros Peninsula's forest. You can't go into this forest because it's a protected area, but we could go into the part of this area, and we can find the mistakes of the method, and we can choose the best ways. So we could find the speed limitations, the weather limitations, and so on. And you can see in this picture the other test sites, another forest. It's in the Bakony mountains, where we made a canopy mapping and spring mapping too. So it's very important. If we want to choose the best platform, it's depend on the spots. If we have independent spots, we can use UAVs, because this is the best solution. If we have a lot of spots nearby, we can use fixed-wing manned aircraft or fixed-wing UAS too. So the high spatial resolution doesn't depend on the platform. However, the surveying speed does. And it's very important because the ground speed is critical because of the changes of the environment and the light conditions, because we have to automate the processes in photogrammetry and the processes in the data mining. So with these modern sensors, we can capture multispectral images up to 600 kilometer over hour ground speed, but we don't have aircraft which can fly with this high speed. So we could make these images with sharp images at 600 meter flight altitude, and by 60 or 100 megapixel resolution with our own sensors. So we tested this methodology, and we can find out laser scanner is the best in the geometry in a case of forest mapping, the canopy mapping. So we could see the photogrammetry methods accuracy with these two methodology. We tried our method in geohydrology in the Bakony mountain range, and we have tested this method in the fields of forestry, nature conservation, population monitoring of herons, environmental engineering in the cities, water management, wildlife and habitat studies. There are a lot of aspects and more and more map results of the same data sets. You can see the same data sets and 5 specific maps on the Sas Hill. This is a nature conservation area of Budapest, the capital city of Hungary. So you can find the limitations in our publication, the latest publication. It's toward the high spatial resolution area monitoring network for nature conservation. You can find the link below. And now I will show you a short video about the monitoring system. It's okay. And now please tell me if you can see the video on my screen. Or tell me if not. So I will start this video.
Risk data, the consistent database of
So I tried to share the voice of the video, but couldn't. Okay, sorry about that. If you have questions, I'm trying to answer it because I had some changes in the system. Sorry about it.
Thank you, Gabor. If anyone has any questions, And you can type it on the chat. I will be available for a while. So thank you again for the presentation. Okay, so now the next presenter will be also from University of Szeged in Hungary. Both seems to be over there. So if you will be the presenter, then soon will give you the role.
Thank you very much. I'm trying to share my screen. Yeah.
Perfect, we can see it.
You can see my screen. Okay, thank you very much. And thank you for the opportunity to show some of the research that we do and that we did in our department based on drone data. My name is Boudewijn van Leeuwen. According to the program, my colleague Ferenc Kovács was supposed to present, but I took it over from him. My name is Boudewijn van Leeuwen. I work as an assistant professor here at the Department of Geoinformatics, Physical and Environmental Geography. And yeah, here at the department we are with 5 geoinformatics specialists, and also with many other geographers from different specializations, so soil scientists, hydrology, geomorphology, etc. And at the department, we usually we are responsible for the data acquisition using drones, and then we have applications that often we use together with our colleagues from different specializations. I would first like to give an overview of the infrastructure that we have here at the department related to the topic, and then I would show some applications in a little bit more detailed. I'm not participating in all of these applications, so the ones that I know most about it that I was participating in, I will show a little bit more, and some others I will just mention. And I will mainly focus on nature conservation and environmental monitoring applications. So at the department we have 2 UAVs. The first one is a Phantom, DJI Phantom 4 that we acquired in 2016 already. And yeah, it's a quite well-known drone. So well, the specs are that we can fly about 20 minutes with it. And it has a payload of 500 grams. And we use this mainly for small data acquisitions. So from areas to up about 30 hectares. We also have a SenseFly EB-X or 10, I don't know how it's called officially. And this one we acquired in 2018. It's a fixed wing drone with a wingspan of 116 centimeters, and it can fly about 45 minutes. Yeah, it can cover much larger areas than the Phantom. The only limitation really is that the maximum distance from the operator is about 3 kilometers. So yeah, this is a limitation. It can also have can be used with different payloads. The EB also supports external RTK data sources, so that means that we don't have to measure ground control points when we are doing the data acquisition. Of course, our drones are officially registered, and at the department we have 3 colleagues with a license to fly them. The sensors that we are using are the following. So for the Phantom, we have the standard RGB sensor with 12 megapixels. For the EB, we have 3 different camera systems. The first one is an RGB camera of 20 megapixels. That's called SODA by SenseFly. The second one is the Parrot Sequoia. Geza already mentioned this camera in his presentation. It's a camera system consisting of 2 parts, an RGB camera with 16 megapixel and a multispectral camera with green, red edge and near infrared bands with a sensor of 1.2 megapixels. And we also have a thermal camera that has an integrated RGB camera RGB sensor, 20 megapixels, and a thermal camera. That is a little bit better than the one that Asa was mentioning, but it's also not very large, the sensor. And finally, we have also a phase 1 camera with a Ronin gimbal. This camera we use now only on a small airplane, but we plan to acquire a larger drone so that we can also use this camera for acquisitions with UAV. We don't fly our drones manually. It's actually not even possible with the EB, but also the DJI we only fly pre-programmed with a pre-programmed flight path. We use drone deploy for the DJI and eMotion for the EB. Also the eMotion we use for post-processing of the RTK signal. For the processing of the acquired data, we use many different software packages, but mainly Agisoft or Pix4D. Yeah, we process the data to, we use raw data in our applications. We also process the data to derived data like NDVI calculations. Of course, we generate point clouds and digital terrain models, digital elevation models, and we also process the data to acquire or to get calibrated temperature data. So let's get to the applications. The first application in our department is the nature conservation application. It is related to invasive species. In many parts of Hungary, we suffer from invasive species that are replacing the native vegetation. Often these invasive species were introduced by humans, and yeah, they are replacing the indigenous species on the Hungarian plain. And this is resulting in ecological and financial losses as well. We identified 7 main invasive species, and we have different research projects here at the department that are dealing with them. One of the projects is that we executed was based on color infrared and RGB orthomosaics. We classify this data and we acquired this data in the Kunshart National Park. We classify this data using different techniques. We were using simple slicing of indices. We're using traditional classification techniques like maximum likelihood classification, but we're also using machine learning algorithms like support vector machine and artificial neural networks. So in this way, we managed to map the spatial distribution of the invasive species, different invasive species. And we compared these results with classifications that we did based on Sentinel-2 multispectral data. And we are also using the results of the drone as ground truth data for classification of satellite data. A part of the research that we are doing is also done with spectral data from an external partner. And this data we also classify and use in our machine learning algorithms. Another example of nature conservation is the habitat mapping of lesser blind mole rat. This animal is digging tunnels. And we were using a digital terrain model and RGB orthomosaic to identify areas where these tunnels could appear. And then we combined this with ground penetrating radar to map the actual tunnels. Let me continue to next application, which is inland excellent water floods. This is also type of research that has a long tradition in our department. And we use drone data for different purposes. The first purpose is that we generated a very high resolution digital terrain model from the surface, because these type of floods are occurring on very flat areas where there's hardly no runoff or no runoff at all. And for hydrological modeling, it's required that we have an extremely accurate digital elevation model or digital terrain model. So we generated this based on our drone data, and then we use this as base data for the modeling process. We also created orthomosaics in RGB and also in false color with false color data. And we classify this data to determine the extent of the floods. Furthermore, we also generated NDVI maps to, and those ones we sliced also for water and non-water areas. The final use of drone data is in this application is to validate the data that we generate using satellite-based classifications. So we have a processing chain that is generating inland access water maps for large areas, and then we validate these maps with high resolution drone data. The next application is soil erosion in vineyards. We generated digital terrain models of an area, a study area, where there's a slope, and due to the slope, there's a lot of erosion, soil erosion in these areas. And agricultural chemicals that are used for the production of these wines, they are coming with water, and with erosion, they are accumulating in the valleys. And yeah, we also used drone data to help in this application. Another application, environmental modeling, monitoring application, was vegetation phenology. In many occasions, we monitored a large area, a wheat and maize area, together with our partner from the Cereal Research Nonprofit Ltd. It's their research area, and they have all kind of information about what kind of types of crops are growing there. And then we went there before, during, and many times during the growing season and after the growing season. And we measured, we created orthomosaics, we measured NDVI, so we created NDVI images. And based on these, we also generated digital terrain models. And based on the height of the plants and also on the NDVI values, we calculated biomass or estimated biomass. And we also managed to detect plant diseases in different places in the experimental fields. This was done with EB, and this was part of a larger project, the Water at Risk project. And we have also a book describing these results that I'm talking about now. So this was already an application that has to do with agriculture, but we also have some other precision agriculture applications. To mention two of them, the first one is to replace traditional plant counting. So traditionally, plants, individual plants were counted by humans or by the seeding machine. And we used our drone mosaic as input data for classification using a convolutional neural network. And in this way, we calculate, or we detected how many plants were there in the rows. And yeah, it goes much faster once the model is trained. And we had an accuracy of about above 90, but I think it was 93%. So it's also quite accurate, the results. Another agriculture application is the mapping of drainage systems. In Hungary, during the socialist period, many drainage systems were built. But after 1989, these parcels were often redistributed, and in many cases the drainage systems were not maintained anymore, or it's not known anymore where we can find them. And we used thermal data and digital elevation model that we created based on drone data to detect where underground the pipes are laying. So we managed to map these pipes as well. A more industrial application was the volume calculation of extracted sand for road construction. We were asked by a road constructor to determine if it was possible to find an optimized way of calculating the volume. Traditionally, this is done by calculating the amount of full trucks that are leaving such a sand pit. And then once in a while, a geodetic survey was executed to measure how much sand was extracted. But yeah, we went there and flew several times with our EB and with the DJI. And then we calculated surfaces, the 3D surfaces, and based on the 3D surfaces, we calculated how much volume was extracted. We got very accurate results that were comparable with the geodetic measurements, but unfortunately, it was decided not to use our methodology, even it was also automated, but it was decided not to use our methodology because the geodetic specialists were hired or were employed by the company, and yeah, they needed also their work. So unfortunately, they could not use our methodology. One more application that was one of the first applications that we did with our DJI is the measuring of erosion of saline forms. Originally in 61 stereo aerial photographs were taken of this area, and then based on the stereo pairs, models were created from these saline forms. And then since 2016, we are measuring them with, we are creating drone images, and we are also measuring them in the field with RTK. And we are making models of the shape, the height and the shape of these geomorphological forms. And in this way, we can estimate the erosion. And slowly they are unfortunately slowly they are disappearing. Okay, three last.
We are running out of time, so we will do 1 more minute left.
Sorry?
Yeah.
Okay.
We are running out of time, so
okay. Then I'll only mention the last application here. That is macroplastics in the Tisa River. This is our latest research. At the same time as a satellite 2 overpass was, we were creating orthomosaics with our DJI from artificially created macroplastic pollution along the Tisa. And we are trying to determine to what extent we can classify or identify these PET bottles in the Tisa. Thank you for your attention. I know it was very short and not very detailed. I showed the publications that we have about these applications, but if you have questions, please send me an email or send it in the chat. Thank you very much.
Okay, next presentation from Germany.
Hello, can you see my screen?
Yeah, it's in full screen.
Okay, thank you very much. Okay. Yes, thank you very much. Now I will talk about the application of UAVs for hydromorphological mapping, and thereby specifically using UAVs, videos captured by UAVs. So I will talk about how we can use UAVs on the one hand to map the bathymetry, but also the flow velocity, and eventually to derive the discharge. And this is not just for a small area of a river, but actually entire river reaches. And to illustrate now the methods which we developed within the last 3 to 5 years, I will show you 2 case study sites which we used to actually estimate how well our approaches are working. And the one study site is located in Zajo, Hungary. So this is a site which Laszlo already has studied for quite some time. And the river which we are looking here has a length of about 700 meters. And the other study site you can see on the right side, it's the Pulmaki River, which is located in the north of Finland. And this river has a length of about 1 kilometer. And both of these study sites we were now looking at. And in the first step, we wanted to, of course, estimate the topography. So this is just using a standard photochrometric approach to derive the 3D model. And here you can see now, in this case, we used about 150 to 600 images to do this. And we had here accuracies between 2.5 to 5 centimeters. And you can also very well see here in this image in both rivers or at both sites that you can actually also see that we were able to reconstruct the points under the water surface. But as we already heard in the talk today in the morning by James Dietrich, these points under the water are going to be overestimated in their height. So actually you are underestimating the water depths if you're not considering these effects of refraction. And so what we did in our case, we actually used the tool which was introduced in the morning and by Dietrich, which basically is considering at the camera pose and then tries to estimate how strongly the refraction is impacting the underestimation of the water depth. And we also used another approach, which is by Woodgate, which basically only assigns a correction value based on the refraction index, and also assuming that all the images were captured from Nadir view. And we applied both of these to correct the underwater points. But in addition, we also performed here, as you can see here in this example, an approach that we are not just taking one image, but actually a stack of images. So we actually used the videos which we captured and extracted frames and then co-registered all the frames to the first frame so that at the end it looks like we were capturing all the video frames from the same position and orientation. And then we stacked those images and calculated for each of the pixels then a median value. And this allows us to improve the visibility of the riverbed, because by doing that, we are able to remove some impact of the waves or on particles on the water surface. And now here you can see the result of our reconstruction based on the correction of the refraction. And on both sides, we are now able to estimate the water depth. And you can also see on the left side for the Zajo River that there are some data gaps visible. And this is mainly due to the circumstance that the turbidity is either too high in this case, or the water is too deep. And so in both cases that we're actually not able to see the riverbed. So for applying this approach based on the images and then the refraction correction, we need to see the riverbed. And then we did some quality analysis. So we performed some accuracy measurements here in this case at the Pulmaki River. As you can see on the upper river part, we used RTK GNSS and measured actually the riverbed. And then we compared this to the elevations which we derived from the UAV approach. And as you can see here now in the plot on the left side, the green points are the points which correspond to uncorrected underwater points. And then in purple, these are the approaches by Woodgate et al., which assumes a Nadir viewing camera perspective. And the red points are the ones by Dietrich. And you can see very well that this refraction correction leads to an improved quality of the data. And actually, in our case, we could decrease the error from 17 centimeters in the case of no correction to about 3 centimeters in the case of correction. So now we found the bathymetry, and in the next step, we also want to map the flow velocities, and thereby we use the standard PTV or particle tracking velocimetry workflow. So again, in the first step, we need to stabilize the videos or the frames which were captured by the video. And so we are using actually the same approach which we also use to get the median images for the bathymetry. So we are searching automatically for stable points in the shore areas, and then we are matching them, and afterwards calculating the homography, which at the end allows us to calculate a video which looks like the camera did not move during the entire time. And after now we stabilize the video, we then mask the border region, because we want to detect particles onto water surface automatically. And if you would include the shore area, most of the particles would be detected in those regions, as these are the ones which have the most contrast. And one approach would be now to do this manually. So actually, as we did here, just delineating the water area. And another approach, which we later on used for the automatic workflow, is actually to use the bathymetric point clouds which we have and project those into the images, and then to automatically delineate based on where these bathymetric points ended up in my image, that this is actually the region of the water. And as you can see now here, we used, in our case, the good features to track algorithm, which searches for points with high contrast. Of course, Harris corner feature detector would be another one which you could use. And so this is a pretty standard workflow. And then you are tracking these detected features from one frame to the next frame. And in our case here, we used the Lucas Canade feature or matching, and other ones would be normalized cross correlation. But at least at this specific case, both algorithms performed in a similar manner. And after we performed now this tracking, there are still lots of outliers in our tracks possible. And therefore, we are performing some further filtering of our tracks. And in this case, we perform some assumptions of how the flow would usually look. So in this case, in the first step, we calculate the main flow direction, and then say if the tracks are deviating too strongly from this main flow direction, then they are considered as outliers. Another one would be just to look at the steadiness of your track. So assuming that your particle is actually floating steadily from one frame to the next. And of course, we also look that our point has to be traceable through a minimum number of frames to be considered as a valid track. And all these steps are performed one after the other. And then you can see on the right side, these would be the tracks which are remaining after our filtering approach. And then the last step would be actually, at the moment, we still have all our measurements only in the image space. So basically, we can now talk about having the velocities in pixels per second. But to also scale it and to have then meter per second information, we need to project our measurements into the object space. And to do this, in our case, we have our UAV. And then we have, here in this case, ground control points. And by knowing these coordinates, we can calculate from which position and from which orientation the images were captured. And if I know this information, in the next step, I can actually project my image measurement through the projection center of the camera into the object space, and then we intersect it with the water surface to actually get our particle position in the object space. And by doing this, we at the end actually get the velocities in meter per second. And all these steps, which I was now explaining, you can also try out yourself. As with this Flow Velo tool, which has also a graphical user interface, you can actually try how that might work in your case for your UAV data. And now I was talking at the moment only applying these approaches to a very short, a small area of interest, which is captured by the UAV, as if the UAV would be hovering at one position, and then doing the velocity measurement. But of course, I was talking at the beginning that we want to do this for entire river reaches. So what we did in the next step, we are now flying along the river in a very slow, with a very slow velocity. And then we are capturing a video constantly. And afterwards, we are taking the video and extracting so-called head frames in a predefined interval, and also the tailing frames to these head frames. And then we are doing actually the similar processing steps, which I was already talking about. So we are co-registering the frames, so the tailing frames to the head frames, and then we go these separate steps. On the one hand, we are putting these co-registered frames and then filtered frames to get the median, or to get these median images, and then this all is put into the standard structure for motion photogrammetry approach. And afterwards we do refraction correction, and at the end actually get the bathymetry. And some parts of this information is then also needed for the velocity. So for instance, the bathymetric points, we are then using to project them into these images also for the flow velocity and to mask the water area. And this is done fully automatically. And at the end, we can get the flow velocity measurements of entire river reaches, as you can now see here in this scenario. And of course, again, some accuracy assessment is performed. And in this case, this is now shown for the Zayo River, where we did ADCP measurements and then compared the value to the UAV data. And we could reach an average deviation of 0.048 meters per second. And the last step now, we have the bathymetry, we have the surface velocities, would then be to actually calculate the discharge. So this is now shown here for an exemplary cross-section, which we extracted from our topographic and bathymetric point cloud. And then we consider the surface flow velocities, and based on that information, we calculate the discharge. And in our 2 case studies, for the examples we've chosen here, the deviations are between 8 to 10% to our reference measurement. But you can also see here in these green values that the discharge estimation is actually very sensitive to the accuracy with which we are actually extracting the cross-section. So we have to get the water level very precise, and then to get the correct river cross-section for the discharge estimation. So here's quite some potential to further improve this processing to get by, for instance, getting a better estimate of the accuracy of the water level estimation. And what would be now the next steps? Of course, one thing would be that now we can do this automatically of these entire river reaches, is to go to the rivers regularly and to capture now the flow patterns during different water levels situations. As you can see now here, this is again for Zayo. On the left side, this has been a very strong flood event with nearly bank full discharge. And on the right side, you can see the low flow conditions of the surface velocities, and you can very well see how here now the main flow is actually changing within the riverbed. And this can then be extended not just to two-time comparison, but actually to do to look at the flow pattern during an entire floods event. So this has been done here, where we captured the video at low flow, and then during the rise of the water level and then the decrease again. And you can now assess these surface flow patterns. And actually in the next step, which we are doing at the moment, is comparing this information to hydrodynamic modeling to actually, so we have now a lot more observations to see how the hydrodynamic modeling is actually fitting to the surface velocity patterns. So that would be from my side. Thank you for your attention.
Thank you. Any questions in the crowd or in the chat? If not, then thank you. Now the last presentation for this afternoon talk. No.
afternoon. My name is Ilya Kocek and I'm from Bulgaria. I'm a marine researcher representing the Institute of Oceanology and also the Association of Geomorphologists in Bulgaria. So our team is very active in the field of geomorphic and habitat mapping of the coastal zone, which is identification and subsequent compilation of maps regarding the habitat pattern and the geomorphic pattern of the submarine slope and the coast. Okay. So in a nutshell, geomorphological mapping, when it's combined with systematological mapping and with biological assessment of the floral and faunal assemblages and communities of the underwater spaces, represent the background of seabed habitat mapping. When we're discussing terrestrial habitat mapping in the coastal zone, it is also a combination of geomorphological mapping and vegetation mapping. This is the essence of terrestrial coastal habitat mapping. So in a nutshell, geomorphic part is of local features of the shallow seabed are corresponding to important marine habitats that are subject to assessment of their good environmental status. This is done in compliance with the European Marine Strategic Framework. All regional countries in Europe are obliged to institute such a about their marine waters in the perspective. On the other hand, coastal beaches, dunes, erosion cliffs, etc., they also host important natural habitats that are preserved in compliance with the habitats of the Union, as they are habitats. They are both to protection under the European and Bulgarian national legislation. These habitats are related to the occurrence of erosion or abrasional and positional coastal sectors. These sectors are characterized by intensive spatial dynamics and rather intensive morphological changes. Therefore, they require regular coastal monitoring and frequent mapping service. We started using drones in 2019 with the Victor one. We built unmanned aircraft, and also we later purchased a DJI Phantom 4 RTK drone. The study area is one of the 52 coastal segments where we are conducting our studies on the Bulgarian coast. I have chosen the Bulk Cove. A cove is a small bay with semi-spherical form. This is from geomorphology, coastal geomorphology. I have selected this area because this study area, the Bulk Cove, because it is located in a cross-border region that is shared between Bulgaria and Romania. This is the Maritime Ocean. Also, Bulk Cove is within the boundaries of nature and archaeological reserve. Also a constituent part of the Natura 2000 protected site named Kalyaka. The area is with all the cover, therefore it is ideal for drone mapping. The dominant kind of terrestrial habitat is the graphitic steppes. There is a lot of open karst terrains, limestone cliffs with many erosional and depositional coastal landforms. So the drone mapping service they usually start with permission by the national aviation authorities. Planning of the flights, establishing of air control points, such on the seabed, which is a shallow cove with no more than 2 meters of depth. Executing the flights. After that comes the processing stage, as most of you are familiar. With the generation of the DES whatnot, the extraction of the TSM, and orthophotomeasuring and also the generation of 3D tile model
which is used for further analysis in GIS. So these drone-derived data products are subsequently integrated into ArcGIS and global number, the software used for cartographic and for analysis purposes in GIS. Preliminary data sets on geomorphology and habitats are compiled. They are subsequently improved in the basis of the field reconnaissance, field and marine reconnaissance with the help of geomorphological archive data, methodological and geological data, also data that is coming from the biological sampling. And this is how the final maps are produced. We produce 4 types of maps. This is a map of the identified land platforms with the red rectangle are illustrated the platforms in this area. This is a map of the corresponding habitat types. Pursuant to the geological classification. Once again, with this red rectangle are shown the marine habitats. Corresponding habitats according to the classification set to the red data for Bulgaria. And also the corresponding broad habitat types in compliance with the marine strategy framework directive. Here this is to visualize this is a correlation table among the classification systems that I mentioned and also the geomorphic classification. This one is also with the MCD habitat, the MCD broad habitat types. Pursuant to the research framework directive. And this is particularly for the marine area. So, as a conclusion, what can I say? Drones significantly facilitate the process of shallow platform and coastal landform mapping, and also the mapping of the smallness and what vegetation applications, for subsequent interpretation and classification. If we're talking about monitoring, we service and I should point out once again that we started this approach in 2018. Deductions regarding the long-term trends about coastal dynamics in the area will be unsuitable without proper comparisons with historical data. And right now, my colleagues are performing this historical analysis and comparisons. They are usually conducted in the fall and winter months. What can I say from my personal experience and personal observations? There is significant morphological evolution and habitat conversion trends in this particular area, and it is because of human-provoked alterations of the global zone in terms of construction of highly technical structures within the reserve in the past. However, the quantitative dimensions of coastal and seabed change are currently being assessed in terms of how much habitat lost, how much habitat gain there is, the rates of erosion, evaporation, and cliff retreat. Our work is being funded by the Ministry of Environment and Water. We do a framework bilateral agreement with the Institute of Oceanology Bulgaria for monitoring of the marine water sea compliance with the Water Framework Directive for Thermal Research Framework Directive. Also, our studies are partially funded by the National Science Fund of the Republic of Bulgaria under contracts for financial aid of young postdoctoral researchers and students. Thank you very much for your attention. I hope it's been interesting to you.
Okay, thank you very much for the talk. So this was the third block, so it's time for the second coffee break, and we have a small delay, so we have the last block starting at 4:40 instead of 4:30. One more quick question for those of you who have not confirmed yet your attendance at the Calvin tomorrow. Please try to decide during coffee break and let me know or our colleagues know when the registration is, because I have to order the meals tonight for the total number. Thank you.
Excellent. Thank you very much. My name is Lance Brady from the United States Geological Survey, and I'm going to give a brief overview. I have a bunch of slides to go through, so I'll go through them pretty quick. But I just kind of wanted to give a basic overview of the United States Geological Survey's UAS program and talk a little bit about the policies and regulations that we're under and the different projects that we've been working on the past years. I've been doing photogrammetry and UAS work since about 2004. And currently I work with the United States Geological Survey, and we're the science arm of the Department of Interior and the federal government. And when you look at the map there of the United States, 1/5 of the landmass of the United States is managed by the federal government for and behalf of the American public. So they are considered public lands. And so it gives us a pretty big responsibility and a large amount of acres or hectares that we have to manage for multiple resource objectives. And you know, our focus is really the uncrewed or the unmanned aircraft space. And so our focus in our office is really the 1,200 foot above ground level and below type missions. We have other assets in our arsenal that we can pull from to gather imagery and different data, whether it be satellite-based systems. We run the Landsat program, satellite program, but we also have, you know, traditional manned aircraft fleet as well that we can call upon to do some higher level stuff. And then I have 1 or 2 slides talking about some of our stratospheric missions that we're assisting with out of our office. So the National UAS Project Office was created in 2008, and really it was to explore the use of the technology at a more formal type project than what had been done previously. We had flown some volcanic missions in the early 2000s, and it really demonstrated the ability of these systems to get into areas where our traditional aircraft just had a difficult time due to safety issues. We soon acquired some old military equipment in about 2009 and became trained by the military in using those systems. However, they weren't suited for doing scientific missions. And so we soon moved to newer systems that were more designed for the type of missions, the natural resource missions that we normally conduct. And kind of the framework that we have the authority to operate. Our national airspace is governed by the U.S. Federal Aviation Administration. So that's our base policy that we follow in what's called the Part 107 regulations. From there, we have step down policy and guidance with the Department of Interior, who we work under, the Office of Aviation Services, which manages all fleet aircraft, including manned and unmanned both. And then each of the sub bureaus under the Department of Interior have their own UAS program, and USGS is just one of them. This is just a current list of our fleet. We're in our 3rd generation of fleet aircraft right now with the UAS program. We have approximately 177 aircraft. We are in the process of procuring our 4th generation aircraft. And so this whole complement of aircraft is going to be changing here in the next year. We conduct UAS-based training from a safety standpoint. And so all of our pilots are Part 107 certification pilots with the Federal Aviation Administration. We also have our own operator course called the A450 Basic Small UAS course. And then we have additional requirements for currency and proficiency flights above and beyond that. As you can see here, demonstrated going back, we acquired data on how many flights that we were conducting annually. And you can see going back to 2010, we had pretty low flight counts. And then our high flight counts were the years of 2019 prior to the pandemic, which we had over 11,000 individual flights. in missions that we conducted that year. We saw a decrease in those flights after the pandemic. And so now we're starting to get back into kind of our normal operations, and we expect that we'll see a gradual increase in our flights from year to year. We also conduct advanced training. So not only on the operator side, where we have advanced operator courses for flying, photogrammetric missions and advanced sensor missions, but we also have data processing courses. So we have both a basic and an advanced photogrammetry course. We have a LiDAR course. We have other mission sets like our image velocimetry missions that we regularly train our operators in, and other agencies as well, not just within our U.S. Geological Survey. This is just an example. It's kind of a short laundry list of all of our different sensors that we have flown or are continuing to fly. We're kind of the test bed, and so we're the test group that make sure that integration work that's being conducted on our aircraft is safe to operate. And then those aircraft are sent up for approval, and then the Office of Aviation Services within the Department of Interior approves those sensors on our fleet aircraft. So we test and integrate numerous sensors on our aircraft, and this is just kind of a short list of some of them that have been approved. We're continuing to do new integration work and testing from gas sensors to ground penetrating radar. We have multiple LiDAR units that have migrated from this list here over to our approved list. We're integrating, phase 1 cameras, hyperspectral geomagnetometers, and also telemetry, radio collar telemetry antennas. This is just an example of one of our GPR surveys, instruments that we use to do stream bed detection. So this is just a profile of the output from the radar, showing basically the bottom of the stream bed. Through our water courses, our water science mission area really has taken the UAS technology and used it part of their operational status for the next generation water observation system, which is an early warning type of flooding and also snow surveys that are conducted on the ground. And so UAS is just one of their tools that they use in their analysis to inform the public of the status of the different hydrologic features in the United States. This is just an example of one of the LiDAR units that we've integrated and tested. We have numerous LiDAR units that we're continuing to evaluate as they become online. So this is just one of them. It's a Velodyne Puck, but we also have a VX20 and also a Livix Horizon scanner as well. We're just getting into the world of hyperspectral. I have a photogrammetry and a remote sensing background, and I would say that for the most part, photogrammetry and multispectral image processing is pretty standard within a lot of not only remote sensing, but geospatial software packages. Once we get into hyperspectral, it's a very difficult instrument to use. It needs refined calibration. The sensors that we have, because they're smaller, there's quite a bit of noise in these scanners, and it's very difficult to do analysis with them, and it takes a long time to do the analysis, and you really need someone, and there's only very few people in the United States Geological Survey that have the experience to truly analyze the hyperspectral. So we're starting to explore hyperspectral, but it is definitely a very difficult instrument to use, and it takes a lot of time and energy to get them airborne and to collect data. It collects a lot of data, and then the data processing takes a long time as well. This is just an example of a recent project this past year. We were looking at biofilm near San Francisco, California in the Bay Area. So this is an area that we're doing some observations due to potential sea level rise. And here is a low tide condition. And so there's a biofilm mat that's within the substrate, and it's a food source for many avian and bird species and other obligate species. And so this project, we're working with our scientists to actually evaluate the health and diversity of this biofilm. And so this is just one application of the hyperspectral scanners that we operate. This is another example. It's a geomagnetometer that we operated several years ago, looking at subsurface iron. Mainly for this project, it was looking at abandoned oil and gas and water well casings. And so this was just one application for the geomagnetometers that we operated. Another program is by Dr. John Fulton here in Colorado in the United States. In this system, we were working with him on developing, it's called the QCAM. It's essentially a Doppler radar that measures stream velocity and for river discharge. And so he has a scientific paper that he wrote on the analysis of using this QCAM technology for river discharge. And we're working with our partners in Australia right now where they're implementing this QCAM. We're hoping that a commercial company will take it and actually design it and develop it and package it up for use across multiple units within the U.S. Geological Survey. We're moving it to our next generation of aircraft where we'll have additional sensors along with QCAM to include, doing our LSPIV missions and also doing other detection missions, including ground penetrating radar. Also working with Dr. Fulton, he's also in a snow water equivalence study. And so you can see traditional methods of digging these snow pits and a ground-based GPR units where they're trying to measure the density and depth of snow so they can calculate how much water is there. So when we have spring thaw, we'll understand how much water is up in the upper watersheds and the impacts that it has in the lower elevation, the outflow streams from some of these high watersheds. With that, we're kind of moving into doing a lot of these missions with unmanned aircraft, which include, as you can see here, this is a ground penetrating radar unit that's looking at snow depth and snow density. And we are also using LiDAR and photogrammetric techniques to measure the depth of the snow as well, kind of a comparative analysis from multiple flights throughout the year. And you can see multiple instruments installed on DJI M600s here near Winter Park, Colorado. This is just a profile with software called Global Mapper looking at the surfaces that were generated. And you can see that we have ground LiDAR from September of 2020, which is the lower black dots there. And then we have a LiDAR collect that we conducted in February 2021, which is the blue dots. And that essentially shows the depth of the snow between September 2020 and February 2021. The red scattered dots that you see is photogrammetry methods. And you can see photogrammetry doesn't do a real great job of aligning imagery, tie points, and densification of point clouds when you're dealing with snow. And so this is just an example of the different techniques that we use to measure snow depth. This is a recent project we conducted in Arkansas, the United States, along the Arkansas River. This is an older gravel pit that was used for gravel mining. The Army Corps of Engineers that develops sites and flood mitigations along some of our rivers is proposing to turn this old mining site into a slack water harbor for dredging equipment and things like that. So we came in to do a project with the Army Corps of Engineers and the U.S. Geological Survey, where the Army Corps of Engineers and USGS hydrologists conducted both single beam and multi-beam bathymetry surveys. And then we came in after them with our LiDAR unit to create a topographic features. And so that topographic and bathymetry data was combined for the analysis in this project. And we flew basically our photogrammetry mission on top of that as well for validation of our LiDAR point clouds. I mentioned at the very beginning, we're also exploring the use of stratospheric sensors and platforms. This project here was a stratospheric microballoon. It sits in a specific part of the Federal Aviation Administration regulations governing stratospheric balloon flight. So we wanted to be able to demonstrate, being able to target a specific area, launch the aircraft, have the aircraft go over the target area, and then safely model the landing and see if we can conduct that correctly. And why we're interested in doing this is we can cover a large geographic area at a very inexpensive, cost-effective manner. And so we're hoping to achieve 10 centimeter ground sample distance with 3-band imagery with this. We were able to deploy the system last year. We launched it up in the Rocky Mountains west of Denver, Colorado. It flew over our area of interest, which was an old post-wildfire scenario of the East Troublesome fire that occurred in Rocky Mountain National Park. And we were able to recover that aircraft just north of Denver along the Wyoming-Colorado state boundary. And the only problem is it was tested and we were unable to trigger the payload and get it operational. So this mission again will be flown hopefully later this spring into the summer, and we'll hopefully have a functioning payload once it deploys. We're also exploring a high altitude long endurance mission as well, which is an airship and also essentially a blimp, and also a larger aircraft that can stay up for weeks on end. That testing is supposed to happen this summer in New Mexico in the United States. And so we've provided instrumentation, both a hyperspectral and a RGB camera for both of those missions. I'm actually in Moab, Utah right now, conducting missions here on this project. And this is, we're throwing a whole suite of instruments at looking at crypto biocrust, which is an interesting project. So we're doing photogrammetry. We're providing both a 10-band multispectral imaging, a thermal multispectral imager, and 2 of our hyperspectral units. Our GSDs on this specific mission, because we're flying so low, is in the millimeters on the pixel resolution. And so we're hoping, we've done a lot of calibration work and have ground sampling data with ASD spectrometers, both on the soil, but also on the vegetation component. And so this is a joint project with the University of Arizona and other U.S. Geological Survey researchers out of California. And this is just an example of what we're seeing. And this is kind of showing a spectral profile of this soil using the 10-band MicaSense imager and also our 274-band hyperspectral scanner. And they align pretty well, but you can see in the head wall nano hyperspectral, there seems to be a lot of noise on the lower and higher end of the wavelengths. And so that's something that we're aware of with some of this smaller instrumentation. And we're hoping with our next generation of aircraft, we'll be able to operate a better hyperspectral scanner than we're currently operating. We also have conducted smoke plume studies, which is demonstrated here both on ground and using UAS. And you can see the Calabri sensor on the bottom. It's a particulate sampler. And so it's sampling the smoke particulates coming off of the incident. We also do other post-fire wildfire work. This is the East Troublesome fire here in Colorado from a few years ago. We were looking at fire severity mapping post-wildfire event. And so this is just a demonstration of basically photogrammetric point clouds in an animation series. We also flew a yellow scan VX20 LiDAR unit and also a MicaSense 10-band. As was discussed in previous presentations, we're also using particulate image velocimetry. This is just an example of using that technique for surface velocities. And so we're not only using this in our hydrologic systems, but also on our volcanic systems. And I have a demonstration of that at the very end, which is now. So this is the Kilauea volcano eruption. Our office spent over 5 to 6 months of 24-hour-a-day, 7 days a week operations over the Kilauea eruption in 2018 on the island of Hawaii. We flew volcanic gas sensors. We also flew photogrammetric missions and LiDAR missions and water sampling devices. And here's just an example from a peridotophy of the volcanic flow, lava flow. And we also used our image velocimetry methods to calculate the lava flow rates. Here's an example of a hydrosleeve. So it's just a water sampling device that we flew to the bottom of the caldera to sample water that was accumulating at the bottom of the caldera. And so we used the DJI M600 with the hydrosleeve, and they were able, up on the caldera rim, to actually sample the water on site for a chemical analysis. We also do a lot of calibration work and develop best practices for not only our multispectral, our LiDAR, but also our hyperspectral. So we have some hyperspectral and spectral experts within our, what we call Spec Lab. And they are lead scientists within the US Geological Survey that we work with to make sure the instruments that we're flying are calibrated in a way that we can get high quality data out to our scientists for evaluation. Mentioned also LiDAR validation, looking at different things that we can use, whether it be reflector targets, large arrow points with black mats to do some of this validation. And you can also see in the lower left, that's a traditional terrestrial laser scan sphere that we're also testing to see if we can use that system with an airborne LiDAR system for validation. I think this is the last slide, but we also distribute our UAS collected data onto earthexplorer.usgs.gov. This is our clearinghouse for all of our remote sensing data that's being collected both from Landsat satellite imagery, but also from our aerial platforms as well, including derivative products like digital elevation models, point clouds, and information like that. So you can see that when you search through the database, you can go through the digital orthos all the way down, and you can see UAS as a subcomponent. And with that, here is our team. We have a great team that work here at the National UAS Project Office, and you can follow us on Twitter and Instagram, and also there's our website at the bottom. Thank you very much. Appreciate the time.
Thank you very much, Mr. Brady. This is such an honor to hear your talk overseas. So the next presentation will be given by Professor Kamal Jain from India. Are you here, Professor? Who wishes to do the presenter role? So good
evening, sir.
Okay, yeah, we can give you the presenter role.
Sir, my name is Akshay Pandey. I am giving the presentation on behalf of Dr. Kamal Jain. I have done this research, that's why.
You can share your screen now.
Thank you, sir.
Perfect. Thank you.
Good evening to everyone. My name is Akshay Pandey. I have done this recent publication in Computer Electronics and Agriculture under the supervision of Dr. Kamal Jain. Good evening from India. This is our recent article published in Computer and Electronics and Agriculture, an intelligent system for crop identification and classification from UAV images using CDCNN. So I think all we know about the unmanned aerial vehicle, or also referred as drone. UAV is an aircraft without onboard pilot, so the name is unmanned aerial vehicle and controlled by the onboard computers. In 21st century, UAV technology reached a point of sophistication. According to the survey of US government, 75 countries have adopted drones for different applications like packaging, delivery, monitoring, survey, sports, armed attack, etc. drone technology has also left a long-lasting impact on the agriculture industry, like crop monitoring, pesticide spraying, crop stress identification, crop classification, and many more. With the help of crop identification, governments and agriculture managers required information on the spatial distribution and the area of cultivated crop for planning purposes. Seeing the increasing population of the world, it can be estimated that by 2050, the population of crops will have to be doubled. So, precise farming is the single option for sustainable development in agriculture. It means crop classification, crop identification is required. A single tool for identifying multiple crops will reduce the human effort. Further, agricultural lands are stretched at all over the India and world, and it is not possible to find an expert for successfully operating different crop identifying tools. So, if an automatic crop identification tool can be developed, then any non-technical person without any non-technical knowledge also can identify a specific crop without having deep knowledge. To serve the above aim, this work process automatic algorithm for identifying multiple crops using a single deep learning based tool. If we are using UAV for data collection, the benefits are drones are used as large scale farming due to its remote control operation from distance. They are easy to use with basic training. It provides good return of investment without any crop damages. We can use RGB multispectral sensor, thermal sensor, hyperspectral sensor or camera. Due to more than 3 bands, multispectral, thermal, hyperspectral contain a lot of redundant data. And it may happen that due to the large amount of redundant data, the classification result become misleading. So in this regard, RGB images are better than other. So we use in this research RGB images. From the literature survey, some author done classification to segregate crop covering land from non-crop land. Mainly machine learning based bi-level classification is done. However, implementation of machine learning requires huge feature extraction from different complex mathematical operations. This is quite tedious job. Deep learning, especially CNN, is better than, but the possibility of using CNN for multiple crops identification still is unexplored. These are the different CNN learning mechanisms, plain CNN or forward propagation learning. In plain CNN, multiple convolution operation performed. First convolution operation output is served as a next convolution input operation. Residual learning, it is also similar to plain CNN, but after 3 or 4 convolution operation, first input data is also added with the convolution operation for the next input. Just because of this convolution operation or this feature loss is very high in plain and residual learning. In dense learning, it is resolved, which is proposed by us in our research, using both input and output of the previous layer as input to the next convolution layer. This is the overall RGB image, crop image capturing by using UAV. In our study, we used Phantom 4 Pro V2 UAV for data collection with 20 megapixel digital camera. These are the flight planning steps, side overlap, front overlap, and the photo collected. So these are the samples like rice, sugarcane, wheat, beans, and grass, which is collected by the UAV. These are the complete steps for overall processing. The first step is candidate crop region extraction. crop and non-crop regions are segmented for creating proper data set. Size of the captured images by UAV is 5472 multiply 3463648. The candidate crop region extraction and image resize done by Python. And the second stage is the input of the CNN to the candidate region. CNN mainly has 4 operations: convolution, max pooling, flattening, and last one is output. In convolution layer, filters are used to extract feature from the input image. The filter will overlap to the input feature map and perform convolution operation. As an output of these convolution operation, new convolved feature map generated. The max pooling operation will reduce the size of the convolved feature map. In max pooling, small elements are selected and minimum and maximum values within this small region is selected as the output. Therefore, the output result of feature map will half of the input convolved feature map. Max pooling is used to reduce the computation time as we are eliminating less important elements from a region and only selecting the dominant or significant one for further processing. Ultimately, flattening is done. This flattening is done, and the single vector, column vector or field are of them artificial for use for artificial neural network. ANN will assign the weights and find out the best probability for the classification for each images. This is the proposed CD-CNN architecture. Here, R1, R0, RL-1 are the feature map concatenation of layer 0, 1 and L-1. FL is the composite function. This is dense block architecture used for the crop identification. It is noted that both input and output will be used for the next layer input feature map. The dense block contains a function which perform batch normalization, convolution, as we already discussed, the convolution operation. Now each convolution layer has an activation function to eliminate any redundant outputs. Generally, ReLU and SeLU activation function are used where ReLU makes the negative values to 0 and SeLU modifies the negative values. But none of them changes the higher value above the 255. In this work, we used a new activation function named SL-ReLU is used by merging soft sign, ReLU and logarithmic function to find out the best result. With this new activation function, the overall dense learning process is designed for crop identification from UAV images. Here, the architecture, here 2 dense blocks are used and in between them of 1 conversion block is used. The previous layer of inputs and output are merged as input to the next layer. Here we can see that after the operation of dense block 1, max pooling is performed here in the conversion block to reduce the size of the feature map, and that will speed up the feature map processing, training processes. After the dense block 2, the output is passed through SL-ReLU here. Again, they eliminate the unwanted values and then finally classified with the help of flattening and softmax function. The purpose of the softmax function is to allot probability of each class corresponding for each image. An image will be classified as a particular class if the assigned probability is highest for that class. In this 5 class of crops, we use 2000 total images are used here. Right? From 2000, we use 1400 for training purposes and remaining 600 for testing purposes. Evaluating the efficacy of the proposed model, these are the parameters which are calculated and confusion matrix is generated. So this is a confusion matrix for different methods. Confusion matrix for random forest, for shift SVM, for LXNet, VGG16, VGG19, ResNet, DCNN, dense CNN, CDCNN. So here we can see that this diagonal row shows the best classification accuracy. So here we input 600 image and 376 is classified correctly, and remaining are misclassification. So this is the confusion matrix. This is the performance evaluation, classification accuracy of testing samples from different machine learning, standard machine learning algorithm, standard CNN algorithm, and our proposed dense CNN. So here we can see the highest accuracy in bold. So we can also compare with the other proposed CNN or machine learning algorithm. Our CDCNN showing the best result. The upper figure shows the training process of different CNN architecture. It is seen that training process is stable with rolling iteration. However, training process of LXNet, VGGNet, and VGG16 fluctuation in the training accuracy is more. Other CNN expect CDCNN. This shows good training process of CDCNN. Here we can see that this is the CDCNN process. Further investigation is done. Choose the accurate number of the dense block in CDCNN. So in first, if we are using the dense CNN, means only one dense block is used. The accuracy is 94.80 and the time is 57.4. If we are using the CDCNN, two dense blocks, the accuracy will increase 94 to 96.20. And also the time is also increased. But if we are applying another dense block, means CDCNN 2, then the accuracy will increase only 0.60 and the training time will increase 20% more than. So our CNN architecture, CDCNN, best showing the best result. This is all the activation function comparison. So CDCNN work with ReLU. CDCNN also accuracy with SELU, and CDCNN with our new activation function SL-ReLU, soft sign logarithmic ReLU. So here we can also see that the accuracy is 96.20, and these are all the parameters. And this is the graph which is showing the training process, training accuracy in per unit. So in view with the aim of crop identification and classification processes, in this article, initially high resolution UAV images are collected for different croplands. A new CNN architecture named conjugated dense neural network is proposed with a new activation function named SL-ReLU present in the convolution layer. The training time is significantly lesser and accuracy is high from standard CNN. So now we are able to identify multiple crop using single tool, which help policymaker, manager, and also farmers. Thank you.
Thank you very much. If you have any questions, please type in the chat. Thank you. Okay, so now moving back to the stage for the in-person attendance. So Nicholas, I think you are the next president. Thank you, Laszlo. Hello, everybody. My name is Nicolas Santos. I am a PhD student at the University in the Remote Sensing Laboratory under the supervision of Professor Jan Dor. This presentation is entitled Transfer Functions to Predict Soil Surface Acceptance from Laboratory Soil Structure Libraries. Actually, this work is a continuation of another work entitled Mapping Water Infiltration Rate using ground and UAV infrastructure data against Valento, Italy. The purpose of the IAQ project is to reduce the gap between satellite observations and local needs for a better management of water resources. Here in this diagram, we can see a satellite that can differentiate between different objects just by recording the spectral signature, for example, water, vegetation, and minerals. The advantage of a spectral solution is the possibility to obtain a continuous spectrum, and in this way, it's possible to see in a good way spectral absorption in relation to the multispectral resolution. And today, there are several initiatives to create soil spectral libraries. This is because soil spectral libraries can be used as training platforms to predict soil attributes using machine learning algorithms. And then these models can be executed into aerial, satellite, or drone images to then generate maps of soil attributes. Just to give a short definition, soil spectral libraries are large datasets that contain spectral signatures together with physical and chemical measurements of soil attributes. The problem is that as soil spectral libraries are created with samples that are collected to the laboratory and must undergo a sampling procedure, it is not clear if these samples represent the remote sensing view from the sky, because satellites, drones, or planes see the undisturbed soil samples. And in the laboratory, the samples are air dried, sealed, and more other procedures. So in this study, we focused on the water infiltration rate because it's a soil surface dependent property. Kirchhoff defined the water infiltration rate as the length units per time units of water entering into the top layer of the soil. Why water infiltration rate is so dependent on the soil surface condition? This is because when the raindrops fall and get in touch with the soil surface, the soil particles jump up, and then those particles that are heavier fall before, and then those that are thinner, and this process is repetitive and cumulative, and this process fills the soil. This is an example of a sample that was measured in the laboratory and the field, and also the ratio of the spectral signature between the laboratory and the field. And here in the ratio we can see what quantitative spectral properties we can lose after sampling procedures. Between them we can mention organic matter, iron oxides, hygroscopic water, and clay minerals. So in this study, we created a data set composed of laboratory and field spectral measurements and also water infiltration rate spectral measurements. For the field spectral measurements, we used this apparatus. The name of this apparatus is Spectro. And this is a closed chamber with a stable illumination and stable geometry, and we connect the spectrometer to this apparatus to obtain field spectral measurements without atmospheric attenuation with laboratory quality. One picture with spectral measurements of the AFD spectrometer connected to the soil drum. A picture of the mini spectrometer, which is the apparatus that we used for the infiltration measurements, and pictures of the fields from which we collected the samples to create our dataset. This dataset represents Mediterranean soils. We collected samples from 3 countries, Greece, Italy, and Israel, from 6 different fields. The locations of the fields as shown here. And for our analysis, we divided the dataset into 3 different groups. One containing all the samples, just to check the generic approach without considering the texture of the samples. And then we divided into 2 groups. One with the most sandy samples and another with the clayist samples. So, in order to check more scenarios, we also had to sample spectrally the spectral signatures to the Hoover spectral solution, which was the hyperspectral camera on board a drone. So we examined spectral basis models using the original spectral solution of the AES spectrometer and also using the Hoover spectral resolution. And then one of these models was selected to be executed into the drone image. Then, after we masked the vegetation, 100 pixels of the bird soil were selected randomly to generate interpolation and execute and get this star hotspot analysis. The random selection was necessary because there was a misproportion of the points after masking the vegetation. So after interpolating the points, it was possible to obtain a smoother interpolation and a better map. Technical details about the flight mission. The Hoover measures the reflectance in the visible and near infrared spectral range in 125 bands. The drone was a Carbon Core Cortex X8. The mission was performed in Aletto, Campania, Italy. The altitude was 138 meters, pixel size of 5 centimeters, etc. This diagram was also presented by Jan previously. Just to summarize, all what I said before, just over word calculation, there is texture determination. And this is important just to generate the roof and also for calculating the water infiltration rate. The classification of the texture is also part of the equation. Spectral measurements in the field and in the laboratory, comparative analysis, then we resampled all the data sets also to the Hoover spectral resolution. We generated different groups, and then we selected the clay group after resample to the Hoover spectral resolution to execute this model to the drone data. Then the vegetation masking, map, random selection of the pixels of the points, IDW interpolation, and then spatial uncertainty analysis. We also performed a ground truth stage with spectral observations and also to compare the measured values of the water infiltration rate against the predicted values of the water infiltration rate of 5 samples that were not part of the validation stage of the model, and also were exposed to the drone view. Here we have 5 validation targets. We can see here white panels with black agricultural nets that were folded in different degrees of darkness to generate artificially different targets under controlled conditions. As shown here, the field against the drone observations are very similar in all the cases. So we can say that
the drone data can be related with the field data. These are the results of the partial least square regression models to determine what the configuration of for the components and also what preprocessing we will use. We check the different preprocessing and a number of components, and we selected the combination that provided the highest results in the validation stage of the field level. So then by checking the beta coefficients, we can check what quantitative spectral properties we can lose after the sampling procedures. Just to summarize these results, we can say that the field domain provided higher accuracy than the laboratory in many cases. It was possible to obtain a good generic model using the ASD spectral resolution, but once we decrease it to the Kubernetes spectral resolution, the accuracy of the validation stage decreased considerably, and this is because of the contribution of the shortwave infrared spectral range that was very important in the ASD spectral resolution for both the field and the laboratory domain. Nevertheless, when in the quality solution, when we separate the dataset into textural groups, we can obtain high accuracies in the validation stage of both the clay and the salty dataset. Here we can see the beta coefficients of the ASD and the Kubert spectral resolution using the well dataset. I will shorten this stage. I want to say here that the beta coefficients of both are very different. So as the models have to profit from different spectral features, indeed there is a loss of spectral information that can be used for predicting soil attributes. And this is a demonstration of the problem of the sampling procedures. Here we can name again spectral features of organic matter, microscopic water, clay minerals, but still they are manifested differently after the sampling procedures. We can say something similar in the case of the sandy soils, and also in the case of the clay soils. Here we can see the execution of the selected spectral-based model that was applied the drone data. In black, the massive vegetation. In red, the lower values of the water infiltration rate, and in green, the target. The points in the left represent the measured values of the water infiltration rate on a 90,000 interpolation. In the right, the points represent the randomly selected pixels and also their interpolation. So here, just visually, we can say that there is a nice similitude when we compare the measured and the predicted values. And this is a hotspot analysis. We can say in the left that the 21 points, as we collected in Aneto, was not enough to perform this analysis, because the idea here is to represent significantly the areas where the water infiltration rate is significantly high or low. But as the Geddes-Ortiz star method considers the values of each entity and also the values of the neighboring points, 21 samples was not enough. Nevertheless, when we considered 100 samples, it was enough, because we can demonstrate significantly the areas where the water infiltration rate can be low or high. Then we selected these samples that were exposed to the drone view, and we can see that there is a nice trend between the measured against the predicted values. So the conclusions for this first stage, I continue then to the other paper that is shorter. This study showed that the structural suspect is a good tool to predict the water infiltration rate. The data coefficients reveal that there are several quantitative spectral properties that are loose after sampling procedures. The field level provided higher accuracy than the laboratory in all the cases. Although it was possible to obtain a good generic model using the optical range completely, including the shortwave infrared spectral range, with the Uber spectral resolution, this was not possible. Nevertheless, by separating the data set into spectral groups, this was possible. And the predictions of the drone were satisfactorily predicted. So then the idea was to predict the field reflectance using the laboratory measurements. So in short, the idea is to use as input the whole spectral data of the laboratory to then predict separately each band of the field level. Let's say if I need to use 200 bands in the field level, I have to generate 200 models. And then the predictions were smoothed using the statistical method. So for this end, we selected a validation group of 10% of the samples. And this procedure was validated using two indicators to check the spectral similarity. One of them is the SAM, spectral angle mapper, and the other one is the ASDS, average sum of deviation squared. In both, lower values indicates higher similarity. So here we want to see the blue distribution close to the lower values. And this is what we obtained here. In both indicators, SAM is ASDS. Here some results. Here we want to see the black spectrum close to the blue. So we see that in all the cases. The samples, they are just representative cases of the validation group. The root mean squared error per wavelength evaluated two relationships. The field against the transfer function, that's the laboratory measurements after the execution of the transfer function, and also the field against the laboratory without the transfer function. And across all the spectrum, we can say that the field against the transfer function provided lower root mean squared error. Just in the initial spectral range, there are short region where the root mean squared error are quite similar, but the improvement is marked. Then the idea was to predict the water filtration rate using a random forest spectral based models, and we found the strength. The highest performance was obtained in the laboratory level, then by the transfer function, and finally by the laboratory. Thank you.
Question? Very nice job. As far as I understood, in any case, the fact that the Kubert stop at more or less 1,000 nanometer is something that is limited in your approach. So, I mean, you need the sphere to have a good result or not. This is one question. The second question is when you rearrange the ASP measurements to the band of the Kubert, did you take into account the relative spectral response of each band?
Yes. The spectral sampling was performed considering the bandwidth of each band.
Okay.
And regarding the first question, please again, it was.
It was, I mean, the Kubert stopped at 1 micron. The data links of the wavelength at 1 micron. But usually when you have to analyze the behavior of the spectrum using the SDURL to the up to 1.9 micron. So you the sphere band also.
No, I didn't use it the models that consider the wall optical range. I used the model that was resampled to the course structure configuration.
Okay. So the fact that you cut at 1,000 nanometer is not
from 1,000 to until 2,500. It's not relevant. I checked that just to examine the contribution of the shortwave infrared spectral range. Okay. And I believe that this is an important challenge for drones because the sensors for this spectral range are heavy.
Yeah, I know. Thank you.
Thank you.
Okay, other questions can be discussed directly with Nicholas. Thank you, Nicholas, again. Thank you. The next one is from Martin from UK, Glasgow University. Stage yours.
Oh, certainly, thanks. Okay. Thank you very much. I'm not going to try and I'm going to try not to keep you too long because it's been a long day. So I'm going to try and fly through mine a little bit. My name is Mark Jolly. I'm from Newcastle University, and today I just wanted to talk to you a little bit about a paper that we released at the end of last year about image symmetry. It's very much today what I'm trying to do is promote two things. So one, the paper, two, a way of thinking. And I think James said this morning about the importance of the easy instructions that comes with software and the open sourceness of things. And that's exactly what I try to do with my work. So the paper that I published last year is open source, anybody can access it. But it just summarizes the key points that we consider when we're using PIV or PTV methods. I reference a lot of people that are actually probably at this meeting, so I'm not going to go into too much detail about the actual ins and outs of things. Just what you can expect to find in the paper. So many of you might have students that look at image velocity methods, so this would be kind of like an introductory to that for them. So the motivation behind the chapter was really to give an introduction to velocimetry, especially to those who may not be too familiar with techniques. So by looking at the generalized processes, the aim of the review was to present and discuss the key challenges and considerations when trying to apply image velocimetry data within fluid field settings. So to do this, I decided the easiest way was to break down the process into 4 key stages, and that's capture optimization, pre-processing, processing, and post-processing. So like I said, today's talk, we're going to focus a lot more on mobile platform methods and what's important when you're capturing data through the UAS systems. So the key stages defined previously were further broken down. I'm just going to touch on some of them. Just the most important ones that I found, especially for UAS systems. The paper covers all of these topics you can see on the board, but I'm just going to be selective and try and fly through as much as I can in as quick as time as I can. So starting with stage 1, which is the capture optimization. This is further broken down into subsections and subheadings, starting with platform choice. As I discuss each of these subheadings, I'll try and go into a little bit of detail what they mean, but the main focus is what they mean with velocity techniques and UASs. So for this one, capture rate I left out because it's not as important as the others. So platform choices, as you can guess, we're going to be talking about mobile platforms, but you can also use fixed cameras. The fixed cameras you tend to install for long periods of time, usually the studies that involve discharge drone curves and things, but usually UAS systems such as the range of DJI drones that people have mentioned today, or any other image capturing device can be used. So using UAS systems to capture image data simplifies a lot of things. It's naturally images are captured at the 0 angle, which reduces the stretch of pixels. That's something I'll talk about in a minute. But also helps the operator capture data in areas that might be too dangerous to traverse, so hard to reach areas, especially in circumstances where there might be high flow, such as flooding. Just quickly going back to the stretching pixels. So GSD is the ground sampling distance, which is simply the distance between 2 adjacent pixels. Typically it ranges between centimeters through to tens of meters if you're using satellite imagery. Without changing hardware, there's 2 main ways to improve GSD. That's either decreasing the distance between the camera and the river, or increasing resolution. So regarding the height, obviously it depends whether you're using a fixed camera or mobile camera. It's a lot easier with drones because you can alter that very quickly. But with fixed cameras, you've got a hell of a job to reset and recalibrate everything. So UAS is definitely better option for that. There's very little research defining the resolution that you should use when performing image velocimetry. A lot of research shows that it doesn't necessarily improve your accuracy with the higher resolutions, but it definitely increases the processing time and storage requirements that you have. And again, it's really hard to suggest optimization of GSD without considering the site characteristics. So the best way to go around this is to actually look at the constraints that you've got in your study. So what sort of platform you're using UAS, what obstacles might you find on the way, what vegetation would impede that, and how big are the traces that you typically see. So ultimately, you have to play about with all of these variables until you achieve the best possible GSD with the minimum amount of resolution. And that's unless you've got unlimited storage and unlimited processing time, which I very much doubt many academics do. So these are actually some of the equations that we use to determine GSD. These are all in the paper. This could be really useful when you want to work out the height of these set cameras to achieve a certain GSD. So the equation on the left is station is for cameras that are captured at a zero angle with no angles introduced in either direction. With the equation on the right, you can introduce two angles, one in the horizontal and one in the vertical direction, and it just splits the image up into 4 grids. Which I tried to implement in a simple spreadsheet tool which is available on GitHub for anyone who's doing anything like this. It just helps you think about sort of resolutions and focal lengths and camera sensors and things that you might need to think about when capturing a certain GSD. Still a bit of work in progress though, so please feel free to have a look and slate me if it's wrong. So next up, we have traces or seeding. So research says that good practice traces need to be present on at least 10 to 30% of the surface of the river. It also needs to remain visible and traceable throughout the sequence. There's quite a lot of work going to seeding at the moment. And it's all still very relevant, but we do know the more traces you have, the better the accuracy of the results. That's a given. So they should also so finally, impact optimization is important to consider the environmental conditions, and this is something that's quite relevant with my study at the moment. Some of the environmental conditions that I tend to focus on are presence of wind, rain, and glare that you find in imagery. And although they've been mentioned in a lot of case studies, they actually get rejected as data for a lot of them, as it's quite hard to actually process any videos that have that in. But that's not realistic in the real world. You're going to have sometimes where there is a bit of rain that might disrupt traces, or there is a bit of wind that changes the trajectory of the traces. So this is actually where a little bit of my study is going to. How can we start to quantify some of that? Which takes us to pre-processing. So again, I'm just going to try and fly through some of this. There's 2 main parts I want to talk about today, which is important for UAS systems, and that's image stabilization, which we've already covered today a little bit, and author rectification. So image stabilization has 2 main methods, manual or automatic. Both work well. Automatic can be a lot easier, but it does increase the processing time that you have with some of your velocimetry. It's also worth noting that there's a vast amount of movement within the frames. So if you're driving through a lot of wind or because you're moving it down the stream, then you can update reference frames, or you can simply just use the first frame, whichever works best for you. There's a lot more detail on types of stabilization within the paper, so if this sort of interests you, you can have a look. With UAS systems though, it's important to know that every video should be run through stabilization, even if you don't think it's moving, because most automatic methods work great for this. It does make it a little bit easier and more accurate. It's what we want. Okay, so another important stage of pre-processing is author rectification. This can be done at a later stage, but for the sake of my studies, I talk about it as an explicit author rectification, which is just applied at the raw video stage rather than later on the result stage. The only time that you don't have to do some author rectification is when you're capturing perfectly at the nadir, which is what we tend to do when we're using UAS systems. But sometimes the camera is still and does introduce angles, or sometimes you might need to capture a specific angle. So you need to start thinking about author rectification. So about author rectification, you also need to look at GCPs. So these are just ground control points. Research shows that you should have at least 4 in the immediate area of the area of capture, and at least 8 across the whole image. So the third stage of the image field symmetry process is that processing, so how we actually go about processing video using PID or PTV. So to better understand the method that you would typically use for your data set, I break down the process into 3 separate subheadings, and that's the founding principles, the flow state, and the feature tracking scheme. But I just want to talk quickly about the feature tracking scheme. That's either using PID or PTV. So PTV-based approaches rely on tracking individual particles along profile. Typically, they perform well at low seeding densities. One thing to bear in mind, though, especially with PTV, is the greater number of the traces that you use or that are successfully tracked, the higher the probability of producing an accurate representation of the put surface velocity. But again, it increases the processing time and power. So PID methods use search and interrogation areas within an image to get particle displacements. They're a lot less sensitive to transformation of particles of individual features as well, and they can deal with a lot larger seeding densities. Problems such as arise where you find inhomogeneity or a discontinuity of traces. And after the processing of the data has been done, we can move on to the post-processing. This is then broken down into 2 subheadings, error statistical analysis and discharge. Again, about that was statistical analysis during the day. So to determine discharge from the velocity outputs, it's important to estimate the average depth velocity for a specific cross-section seen within the image. So usually calculate the depth velocity and alpha coefficient is required. You can usually estimate this to be around 0.85, but to get a better representation, you're better off using ATP and some historical data. One issue that we may be seeing when you're trying to calculate discharge is that the river surface that has to have good traces. That's normally a problem when you're using PTV, so you might find you've got a lot of traces in the near field, but not too many in the far field. So one thing you can do with that is extrapolate data or interpolate data to try and fill those gaps, and there's a few methods that you can use. But a lot of this is built into software that you use, so if you're using PID software like River, but sometimes it does it for you, especially in the KLT methods. So the things I want to conclude on today, key takeaway should be that the mobile platforms, they're very similar to fixed platforms, and the paper that goes on through all of this, you can apply to both. But there's an added importance of stabilizing the image. It's also safe to conclude that there's a vast amount of research regarding the optimization for most parameters with traces, stabilization, and author rectification being the key considerations. And the most important finding I've got from this study regarding my research is the lack of information around the influence of wind rain solar radiance on imagery. And that's something that I look at planning to look at in the next couple of months. Just quickly going to touch on how I've used this paper in the past few months. So I did a placement with the Scottish Environment Agency, and from that I created a handbook, and this handbook literally takes you through the entire steps that you need to go from having absolutely no prior knowledge of image symmetry to creating your own fixed site. So this could be great for students, it could be great for people who are trying to use it in their own study and might not know exactly how to go about doing it. It took me so long to understand how to use image velocimetry, going from absolutely no knowledge to where I am now. So this was created for those people. Some of the main things I got from that, just quickly, is going to be, probably don't be afraid to get things wrong. I think that's the main point. So if you're using, so this video is actually taken by an operative of the Scottish Environment Agency using a mobile phone. Could have been a drone, could have literally been anything, but she chose a mobile phone. And I just ran it through some software just to see what sort of traces would be visible on the surface. And then from this, we created a project. There's now a fixation at the site. But again, you could use drones to go out there and start mapping some of these rivers and potential sites. So there's a lot of potential there. And then finally, the last thing to come from this paper was the next stage, which is my SDI environmental factors part of my research. The hypotheses of this next chapter is that trace SVI and dispersity significantly impacts velocity results using KLTID, which is the PTP software. So the main question being, to what extent does SVI and seeding dispersity have on surface velocimetry, and consequently discharge when using PTP methods over a variety of flows, and then that's going to link into the environmental study, which I hope to do later on this year. And that's what this is all about. I tried to make it quick. Thank you for listening, and
the last two talks are coming, and we are shifting back to vegetation. So the two formal questions for tonight. Right? So I think is the next one.
Hi everyone, can you hear me?
Yes, just a minute.
Yeah.
Just a second to present your. Perfect. Thank you. Stage is yours.
Okay. Hi everyone, my name is Adrian. And first of all, I want to thank you, the Harmonious, to this opportunity for letting me talk today. And I want to congratulate them for all the achievements that they are having this cost action. So in this presentation, I will show some of the results reported during my thesis about the development of a phenotyping platform based on a UAV system to apply them in different projects of wheat and maize to study the performance of the different genotypes under abiotic stresses. Right, cannot change. No. So briefly, to put everybody in context and provide a general lines of what is this phenotyping and why we need the drones for doing this kind of operations. So if we follow the trends of improvement of the main stable crops as wheat and maize, we can see that they are quite below from the projected demand that we will require in the future of food. So also this we are in a moment of climate change scenarios that will produce increase of abiotic stresses like water and heat stress or deficiencies of different nutrients that are vital for the crops that will even limit the production of these crops. So what are the strategies that we have to follow to close these gaps of yield so we can improve our productions? So there are two main strategies. One is to continue exploiting the natural genetics variation that we have. So look for new genotypes by, for example, breeding, crossing different cultivars, maybe one with higher production, another one with genes that can give the plant some resistance to different stresses, to have new lines, so new cultivars that can produce more in a more limiting environments. Another main strategy is the adoption of better management practices, like can be changing the schedules of irrigation, or the fertilization rates, or even changing the whole management systems. So we will show some examples. So given these strategies, we are facing that we have to assess hundreds, sometimes thousands of lines, so thousands of new cultivars under different growing scenarios, different environments, and we need some tools that are capable to give us this valuable information of the genotype's performance, as can be measurements of growth, so the development across the cycle, this tolerance that can be will be vital to increase this production under these limited environments, study the architecture, so to give a lot of parameters that can help us to decide which genotypes, which cultivars will be able to produce more under this scenario. So achieving this point, so how can remote sensing, how can UAVs help us in this process? As we have this elevated number of lines to be assessed, we need some tools that can help us to assess all the genotypes rapidly in a non-time-consuming way, so we can reduce the cost, we can reduce the efforts, and we can reduce the effect of the weather fluctuations during the day that can affect our measurements. So in this sense, UAVs are an excellent opportunity to maintain the precision and efficiency of the traditional methodologies, but increasing the throughput capacity, so more lines can be assessed in less time. So if we reduce these costs, these efforts, even we can do more assessments during the crop phenology, and we can have different kinds of information. For example, measurements in the initial stages of the crop. We can, for example, count seedlings to see the germination rate. The germination rate that will also be vital for the final estimations of yield. Or at the end, counting different fruits or fluorescence. In this case, for example, in wheat, we can even achieve the count of ears that will determine our yields. Also maintain a monitoring, so how these genotypes are responding to this environment across all the phenology, or in more advances, other advances models, like can be 3D, we can assess very precisely the crop heat or even the biomass. I want to spend much time here. I'm sure everyone knows about how plants respond to light. So this is spectral, very characteristic behavior. If we assess this information in different bands, we can reformulate a huge bunch of indices that can be helpful to assess different traits, vegetation traits, important to our applications in this phenotyping purposes, so to assess the resistance to these abiotic stresses. In our case, in Barcelona, we used this multispectral camera with 12 different bands, one facing upwards to the sun to calibrate the other measurements. And we formulate different indices that can help us to estimate, for example, the coverage of our crops by assessments of vegetation cover and plot greenness. Also, more specific bands of where pigments absorb light, so we can assess even chlorophylls, very related, for example, with the nitrogen fertilization, or other pigments as anthocyanins or carotenoids that can give valuable information about the resistance to stresses. The PRI, for example, an index based on specific bands of also absorption of lights, can give us information of the photosynthetic activity of our plants. So we can check, we can assess which of our genotypes is producing more under, for example, environments that can limit this production, this photosynthesis, or assess the turgor of our canopies over lights with measurements of water content, so bands related with this turgor of the leaves. So moving now to practical examples. In this publication, we had a challenge that we needed to phenotype plants, in this case, made hybrids in a study in Zimbabwe, where these plants were in a totally different management. So a conservation agriculture that limits the application of fertilizers, for example, in order that they can afford the cost. So they need to change this management in order to try to increase the yield try to avoid the drought stress, so the lack of water affect our plants. So this management involves a minimum soil tillage, but also is characteristic because the surface of the soil is covered because by this vegetation residues. So this is help the soil to maintain the water, also produces gives a bit of nutrient to help the development of the plants. And in this case, we visit Zimbabwe when plants were in a seedling stage, so they were small plants. So this residue cover was affecting our measurement, so we needed to solve that. So here, for example, we decided to calculate NDVI-based threshold. So we decided that here everything up to 0.4 NDVI values was considered as vegetation. So as we can see in this graph, where the PRI is graphed against the yield, we can see how the correlations when the vegetation mask was applied was increased rather than the measurements of the whole crop. Here we avoid a bit the effect of the plant density, and we focused only on the response of our genotypes to the light, so to assess exactly which genotypes were more active in that moment. And here we can see how this was critical to select, to check which ones will have a final grain yield. Another methodology that we have used and I have applied in several studies in my thesis are the RGB-based indices. This methodology, in comparison with multispectral indices that I just commented, have a clear, it's a low cost, alternative to those more expensive sensors. So those indices are based on mathematical models that study how green is our pixels, our images. Here is an example as the green area and the greener area that are counted, so the percentage of pixels that are green in our images. So we can assess easily the coverage of our crops. Even the difference between those indices is that the greener area is a little bit more restrictive, so only assess those pixels that are green, excluding those more yellowish tones that maybe are related to parts of the plant that are less photosynthetically active. So we really focus on small differences between genotypes to see which ones are more active in those limited environments with abiotic stresses. Here is a very good example with also in Zimbabwe assessing maize genotypes, in this case in a more reproductive stages, so plants were more big. Maize plants can be up to 2 meters. So drones are a very good tool to assess this kind of tall crops. And you can see here in the images how the dose of nitrogen application is highly related to the color of the plant. So more green, darker greens are related to those with a higher nitrogen dose. So this kind of methodologies can be really used to check those genotypes with less capacity to use efficiently this nitrogen. Or, for example, in precision agriculture, detect part of our trials, of our our trials where we need to do to make any decision of, for example, adding more fertilizer or apply irrigation or whatever. This is a complex graph, but I just want to zoom in this area where I show the correlations against nitrogen here and grain yield here against the indices that I just commented. You can see how it's highly correlated against both parameters. as canopy-based measurements have been shown in this study and many others as good assessments of crop biomass. So here we are indirectly assessing this crop biomass as an effect of the growing conditions, in this case, nitrogen. So this can help, could be very helpful because it can allow the assessment of how efficient are our decisions on the field. So in this case, fertilization, with that going and reducing the efforts and the cost that can be do manually or going to the lab to process our leaves. Another example, but now with phosphorus. Here we can see the aerial image where clearly the effect of phosphorus is affecting the germination rate, so the initial vigor of our genotypes, and even inside the same conditions here, the reduction of phosphorus, we can see how which genotypes were producing more. Here we can see. I wanted to show these images that where you can compare the ground and the aerial assessments. So it can be seen how the loss of resolution affects the segmentation of what is vegetation or not. The p-value marks that there are significant differences, but the correlation indicates that we are measuring things very similar. Finally, with the studies, we assess. I wanted to show here these two graphs where both RGB and multispectral images were taken, and the correlations were very similar between both approximations. But here with the RGB images, with the loss of resolution flying at 50 meters, we're not able. It was not that worth it to check these differences in the beginning of senescence of the genotypes. So correlations level were better. And in the case of multispectral indices, we compared the DBI measured at aerial level with the green seeker, that is a handheld assessment. And to end, the thermal methodologies are also very useful because they are a direct proxy of calculation the transpiration rates, as when plants have some limitation of water or other things that are affecting their productivity, their photosynthesis, they will close their stomata. So the temperature of this leaf will increase. And the same study of maize, here the use of UAVs.
I think we're running out of time, unfortunately. It's already 7 minutes.
Sorry?
We are running out of time.
Okay. So finish here?
Just maybe about a few remarks.
Okay, so just a couple of slides more. I finish in 2 minutes, right?
It's already 15 minutes now, so we have 15 minutes for each talk.
Okay, so I finish here. Okay, so short time.
Okay, thank you very much. Unfortunately, we have to get the final talk as well.
Sorry.
Sorry for the interruption. We're running out of time. So thank you again, and we have to move on to the final talk. We still 15 minutes over the schedule. So we have Sean ready for the presentation. That's what Yes.
Okay.
Yes.
Can you hear me? So I'll share my screen and try to be quick.
Okay.
So it's been a little bit over schedule, maybe.
Yes. Thank you very much. Stage is yours.
Okay, so I have just some ideas and some progress that we've made on using high resolution UAV imaging for forest productivity monitoring. This was a project that came to me in a collaboration with a couple of people from the university and also the Catalan Center for Forestry Research. So we wanted to establish a protocol to directly quantify pine cone production using remote sensing in some way that would be faster than the current field-based pine counts. This is important because it's a value-added forestry product here in Catalonia that has also quite a good market. So we tried to define the spectral signal or the best combination of sensors for doing this, techniques for capturing images of pine trees to estimate the productivity of tree stands, and I have just a little bit of image processing and results. So this is some first examples. This is of a natural pine forest, and we were looking at ways to segment out the trees. This is with a scientific 4-band multispectral sensor. And this was quite interesting because in a natural pine forest, from the digital elevation model, you could segment the trees separate from other species. But they wanted me to actually count the pine cones on a tree, which I said I didn't know if it would be possible, but we would have to use a higher resolution UAV imagery in order to even attempt that, because we couldn't see pine cones with this sensor. It was an interesting sensor because we could calculate all these different spectral vegetation indexes, which could potentially be correlated with biomass or productivity, except for the masting phenomenon and also their interest in directly counting pine cones in order to control theft. But I did present them with some of these different vegetation indexes and some spectral characteristics, where we had shown that in the red edge and the near infrared, you could separate pine cones. This was an example of the capacity to count the trees and then estimate productivity by tree. But again, we couldn't actually see the pine cones, so that wasn't functional. We started working with more high-resolution imaging in simplified pine stands, plantations grown just for pine nut production. As an example here, where you can see the segmentation of each tree was much simplified, since this is like a row of lollipops once you produce a nice digital elevation model. So we collected with some modified cameras, high-resolution images on the ground in order to apply a fast random forest classification, create probability maps of pine cones, and subsequent code to count pine cones using these modified cameras. This is some examples from the ground. This is examples from the tree. So you can see on the left panel, the little red dots are actually where we detected pine cones. We had good results in terms of counting pine cones that were actually visible on the tree from the UAV imagery. So if we compare here the manual-based, image-based pine cone count with the model, the R² was 0.725. If we compare that with the actual field-based counts, the correlation was much less, and moreover, the slope of the line indicated that we saw perhaps 6% of the pine cones were visible from the native perspective. So we decided to try to work with some more easier to use sensors and speed this up. So we worked with the AgroCam on a Mavic 2 Pro, and to develop some tools with these collaborators in this project to help process this a little bit faster. So this is some examples of a different pine forest with the AgroCam. It creates color infrared, NDVI blue, which is okay for biomass perhaps, but the separation between the trees and the ground was not as good. And then in this pine stand here, you can see the density of the pine stand made it really difficult to segment individual trees and get productivity on a tree land. So we recommended using our mosaic tool, which does originally made for wheat and maize, but here we can separate out trees, separate them manually, and extract the information at the tree level using squares for the DEM and for the NDVI images. And so we're looking at running the same, similar, not the exact same, because it's a different modified camera, high resolution, to estimate pine tree productivity here. And the idea was to create a workflow and a tool within this project that could do that. And so we have to add on to here the machine learning process to this tool that would count the pine cones. But meanwhile, from the Mosaic tool and this small plugin we made for Fiji, you could use the forest scanner to calculate different vegetation indexes related to biomass, or different tree height metrics related to the digital elevation model coming from, or the RGB Mosaic image from the Mavic 2 Pro, or from the modified NDVI AgroCam that can be attached to it, or the DEM coming from either one of them. And so we hope to implement the same machine learning within Fiji, which is called WECA, Fast Random Forest, and see if we can get some estimates, though we're a bit concerned that the perspective may not be sufficient to count enough pine cones to really develop a robust functioning model in terms of field counts to image counts. Lastly, we have some hope for integrating some LiDAR, airborne and ground-based LiDAR. This is a video, which is not working, but I'm sure you've had some experience with this. So hopefully this will help us segment trees, even in close built stands. And that is all. Here are some emails in case you're interested in contacting me, and I will provide the PDF so you can check on the links or reach out.
Very much, Sean, for the presentation. And it seems that this was the final moment of today's workshop. I would like to thank all the presenters, here online and in person, for the exciting drone-based research. And it was a long day, so it's time for rest. And for those who are coming for the working meeting tomorrow, let me highlight that that will be not here, this building. If you check our website, personalmodules.eu, you can find the details where is our Institute of Earth Sciences, and you can find a map as well, and even you can contact me on my phone number if you get stuck or something. We will start tomorrow at 9. Maybe 9. And then there will be a hybrid form of presentation for the vertical meetings. Yes, we will start at 9, with the vertical 1, and then go forward with the rest of the vertical meetings. Thank you very much for being here. Goodbye, everyone.